What if everything you think is real, your memories, your thoughts, even your sense of self, is just a beautifully orchestrated illusion? What if the present moment is already history by the time you feel it, and your brain isn't just observing the world, but fabricating it on the fly? Over the next 4 hours, we'll peel back the layers of your consciousness, revealing how quantum physics, neuroscience, and psychology collide to expose the hidden architecture of your mind. This isn't fiction. These are verified anomalies, truths that challenge everything you believe about perception, time, identity, and choice. So if you're ready to let go of certainty, step into the unknown, and question not just what's out there, but who you truly are, tap like, hit, subscribe, and follow the thread into the deepest recesses of the self, where reality begins to fracture. A particle can be in 2 places at once, until you look. Imagine standing in front of a hallway full of locked doors, each one identical, silent, and unmoving. You're told behind one of them lies your future, but the only way to know which one is real is to open one and watch all the others vanish. That's quantum mechanics, not metaphorically, literally, because at the smallest scales of nature, the world doesn't behave the way your intuition wants it to. Reality is not a fixed path you're walking down, but a shifting landscape that rearranges itself the moment you take a step. And nowhere is this more strange, more mind-warping, than in the simple truth that a single particle, a thing so small it borders on nothingness, can be in 2 places at the same time. Not metaphorically, not figuratively. Actually, until your attention collapses the possibility into one reality. This isn't science fiction, it's science fact, and it challenges not only your understanding of matter, but your sense of meaning, of cause and effect, of what it even means for something to be real. You were raised to believe that the universe is out there, independent, objective, stable. But quantum physics says otherwise. It whispers a deeper story, one that doesn't just tweak your understanding of the cosmos, but rips it apart and reconstructs it into something far more intimate. A world where the observer and the observed are inseparably tangled, where reality itself waits for you to decide what it is. They taught you that reality is solid, that things exist in one place at a time, that you can measure, predict, and confirm the world like a machine built on logic and causality. But that worldview dissolves when you shrink your gaze down to the level of atoms and subatomic particles. There, things stop acting like things. A particle isn't a dot in space. It's a smear of probability, a cloud of potentialities. It doesn't sit quietly waiting to be discovered. It dances in all the places it could be, simultaneously. Until you look, until you measure, until you interfere. And when you do, the particle chooses, randomly, capriciously, instantly. The wave of possibilities collapses. The many paths reduce to one. And that act of collapsing, of pinning down reality into a single state, is triggered not by time, or gravity, or fate, but by something astonishing: your observation. The very act of seeing alters the scene. This is not philosophy. This is experimental physics, proven again and again. Take the famous double-slit experiment. When particles like electrons are fired toward a wall with 2 slits, they create an interference pattern, not like marbles, but like waves, as if each particle went through both slits at once and interfered with itself. But when detectors are placed to observe which slit the particle passes through, the interference vanishes. The particle acts like a marble again, choosing just one slit. Observation destroys the wave behavior. Consciousness changes the outcome. And in this lies the heart of the paradox. Reality does not simply exist, it waits. But what does that even mean? That reality is passive? That the universe is undecided until we ask a question? It seems impossible, and yet the evidence is undeniable. In the quantum world, possibility is more fundamental than actuality. The particle does not have a definite position until you observe it. It exists in a superposition, a blend of every possible state, smeared across the spectrum of existence like paint across a canvas not yet touched by a brush. And when you do look, when you do measure, when you do ask, it's as if the canvas freezes, the paint settles, the picture completes, but not before, not without you. You are part of the painting process. You are not separate from the world you observe. You are embedded in it, entangled with it, creating it as much as discovering it. And this fact, that your awareness might help shape the outcome, does not just shake physics. It reshapes metaphysics. It invites a new understanding of self and world, of identity and time, of what it means to exist at all. Because if a particle can be in two places at once, if the universe allows such ambiguity, then perhaps your reality is not singular either. Perhaps you too exist in superposition, hovering between the lives you've lived and the ones you haven't yet dared to choose. Think about decisions you didn't make, roads you didn't walk, people you never met, versions of you that flickered briefly in the fog of possibility and then disappeared when you chose something else. What if those versions weren't fiction? What if, in some quantum sense, they still echo, still hum in the background of your being? What if identity is not a fixed story, but a cloud of probabilities collapsing moment by moment as you decide who you are? If a particle doesn't become real until it's observed, what does that say about the self? Is the you of today any more real than the one you could become tomorrow? Maybe the very act of deciding, of looking inward, is its own kind of quantum measurement. And maybe the fear that comes with choice, the anxiety of committing to one path, isn't just psychological. Maybe it's ontological. Maybe it's grief for the collapsing of parallel selves. Maybe it's the weight of watching infinite futures condense into one. And in that grief, there is also wonder. Because to choose is to create. To observe is to collapse possibility into presence. To live is to carve meaning out of mystery. Even the very nature of time unravels under this quantum lens. In classical physics, time is a line, past, present, future, fixed. But in the quantum realm, time doesn't behave. A particle can affect its own past. The future can rewrite the present. Causality loops and twists like a Mobius strip. And suddenly, your life is no longer a sequence, but a wave, a pattern, a field of potential futures interfering with each other in ways you may never fully understand. And so we return to that particle, the one in two places. It's not just a curiosity, it's a doorway, a clue, a shimmering crack in the facade of the ordinary. It says, the world is not what it seems. You are not what you seem. And if you dare to look, really look, you will find that the act of looking changes everything. Not just the object, not just the moment, but you, the observer, the maker, the co-creator of reality. So what do we do with this knowledge? Do we freeze in the face of infinite possibility? Do we mourn the paths not taken? Or do we lean into it? Embrace the ambiguity, the freedom, the terror and beauty of a universe that responds to our gaze. Perhaps the lesson is not to seek certainty, but to become comfortable in the unknown. To make peace with a reality that doesn't exist until you engage with it. To find courage in the collapse of the wave, knowing that every choice you make is both a death and a birth, a letting go and a becoming. Because in the quantum world, looking is not passive. It's generative. It's alchemical. It takes the ghostly and makes it real. And perhaps that's your role, not to observe life from the sidelines, but to step into it fully, knowing that your attention matters, your presence matters, your decisions, however small, ripple outward into the fabric of what is. And so the paradox resolves, not in clarity, but in coexistence. A particle can be in two places at once, until you look. And you too can hover between who you were and who you might become, until you choose, until you dare, until you open the door and accept that reality is not given, it is made, in the looking, in the asking, in the wild, uncertain act of being aware. Because maybe, just maybe, awareness is not something that happens inside the universe, but something the universe does when it becomes you. The delayed choice experiment. The future decides the past. What if you wrote the ending of a story before the beginning was ever put to paper, and the plot lines obediently rearranged themselves to match the twist you hadn't yet chosen? What if the ink in the opening sentence only dried after you'd flipped to the final page? That's the logic-defying realm you step into with the delayed choice experiment. A place where the future doesn't just unfold from the past, it loops back and reconfigures it. In this world, causality is not a straight line from A to B, but a shimmering web of influence stretching forward and backward in time, where your decision in the present appears to ripple into the past, rewriting what should already be set in stone. You've spent your life believing that what has happened is fixed, that the past is the foundation upon which everything else is built. But quantum physics cracks that foundation open and whispers a far more unsettling possibility, that the present might edit the past, and the future might cast shadows backward across time itself. Imagine reaching out to catch a falling glass, only to find that your hand had already moved in response a second earlier, as if time had bent to meet your intention before it fully formed. The delayed choice experiment doesn't just suggest this, it demonstrates it empirically, consistently, and irreversibly, and the deeper you look into it, the more the illusion of linear time unravels, revealing a universe in which chronology is optional, in which the act of choosing doesn't merely affect what will happen, but what already happened. To understand this, you first need to forget everything you know about time. We're trained to experience time as a conveyor belt, always moving forward, never pausing, never reversing. The past is gone, the future unknown, the present fleeting and always consumed by the next moment. But in quantum mechanics, time is not a simple arrow. It's a field of interdependencies. The delayed choice experiment begins with the humble photon, one particle of light, and a setup similar to the infamous double-slit experiment. In that classic setup, photons pass through two slits and strike a detector, creating either an phase interference pattern, if they act like waves, or two distinct clusters, if they act like particles. What makes the delayed choice version so disturbing is the timing. The choice of whether to observe the photon as a particle or a wave is made after it has already passed through the slits. And yet, the photon behaves according to the decision made afterward. If the observer chooses to detect which slit it passed through, it behaves as a particle, having gone through one slit. But if the observer chooses not to detect, it acts like a wave, interfering with itself as if it had gone through both slits. The twist. This decision is made after the photon should have already decided what it was. It's as if your present observation reaches back in time and changes the past state of the photon, retroactively deciding what it did. This isn't metaphor, this is experimental data. So what does this mean for reality? For you? For everything you think is true about cause and effect? It means that the world may not be constructed in the orderly sequence we imagine. That time may not be an independent backdrop against which events unfold. Instead, the entire fabric of reality might be woven from correlations, from a vast, interconnected net of outcomes that align not based on when things happen, but on how they are eventually observed. The photon's path isn't determined when it travels, it's determined when it's measured, which means the universe doesn't commit to a single past until the present requires it to. Now think about that in human terms. Think about how often you reinterpret your own past based on what you now know. How a painful memory becomes a moment of growth only in hindsight. How something meaningless takes on significance only after its echo is heard years later. Maybe this isn't just psychology, maybe it's physics. Maybe the brain's tendency to reframe the past isn't a glitch. It's a reflection of how reality itself behaves. Maybe memory isn't a static archive but a quantum process, one that reshapes the narrative every time it is accessed, folding the future into the past, like hands shaping clay from both ends at once. And if this is true, if observation truly reaches backward, then what happens to responsibility? To choice? To identity? We like to think we are the products of our pasts, that who we are was shaped by the sequence of events that led us here. But what if the past is not finished? What if it's fluid, responsive, still vulnerable to the weight of our present awareness? What if the act of understanding, of interpreting, is not a passive reflection, but an act of co-creation with time itself? Then every new insight doesn't just color your memories, it alters them. Every moment of presence becomes a ripple that rewrites the context of what has already occurred. You are not merely walking forward on a path laid out behind you. You are sculpting the road you've already walked. And perhaps this is the deepest implication of the delayed choice experiment. That time is not something you move through, but something you generate through your engagement. That reality is not fixed until you engage with it, not just in space, but in time. Consider the implications. If the future can change the past at the quantum level, what does that say about destiny? About free will? You might imagine your life as a line drawn from birth to death, but perhaps it's more like a painting still being brushed from both directions. Your choices now don't just carve a future, they cast meaning backward. They highlight certain memories, diminish others. They reach into your past and alter the emotional resonance of things long since done. And maybe, on a level far beyond introspection, they literally shift the physical chain of events that led here. If the fabric of the universe holds space for such retrocausality, then your story is not yet finished, even in the parts you thought were over. Every moment becomes a negotiation between what is and what was, and observation is the bridge. This doesn't mean you control time like a god. It means you participate in it like a partner. You are part of the machinery, not outside the clock, but in the gears, turning the hands from both ends. And still, this leaves us with the haunting question. If the future can decide the past, then what is the now? What is this moment you call the present? Perhaps it is not a thin slice between what has been and what will be, but a crucible where both are forged. A meeting point where the past collapses into a single story only when the future has made its demands. And perhaps this explains the sensation of déjà vu, of prophetic dreams, of intuitions that feel impossible to justify. Not fantasy, not coincidence, but subtle entanglements across time, echoes moving in both directions, signals from outcomes not yet realized, rewriting the context of what came before. And if this sounds like science fiction, remember, the delayed choice experiment is not a theory. It's an observation, repeatable, measurable, real. The photon behaves retroactively based on a future choice. The universe answers questions before they're asked, and if a single particle can rewrite its past to match a future decision, then perhaps so can you. Let this truth change the way you see your story. The moments you regret may not be as fixed as you think. The traumas, the mistakes, the silences, they might still be open, still waiting for a different context to collapse into, still capable of becoming something new under the light of a present intention. Maybe healing is not rewriting the story, but observing it differently, choosing to measure it in a way that changes its form. Just like the photon, just like time. Maybe the past isn't the prison you assumed. It's the raw material of meaning, sculpted not by what happened, but by what you choose to make of it now. And maybe, in some quiet, impossible way, the universe is always waiting for you to choose, not just what will happen, but what already has. Observing something changes its reality. You walk into a room full of mirrors, but none of them reflect you back until you make a move. You raise your hand, and only then does the image respond. You tilt your head, and the mirror scrambles, reconfigures, recalculates before offering a version of you that wasn't there a moment ago. Now imagine that the world itself behaves like that mirror, not passively reflecting, but actively composing itself in reaction to your attention. This is the haunting elegance of the observer effect. The idea that the simple act of watching something, of focusing your awareness upon it, fundamentally changes what it is. Not metaphorically, not symbolically, but physically, tangibly, empirically. In the realm of quantum mechanics, Particles don't merely sit around waiting to be seen. They are unsettled by your curiosity, reshaped by your gaze. They live in a haze of probabilistic possibilities until your measurement pins them down into a single outcome, collapsing their ambiguity into a precise state. But the true disruption runs deeper than physics textbooks let on, because this isn't just about electrons in a lab. This is about you, your relationships, your choices, your identity. This is about how everything you observe, people, events, memories, bears the fingerprints of your perception. The observer effect isn't some obscure feature of subatomic weirdness. It's a mirror held up to the nature of awareness itself. And once you see it, once you understand that observation is not innocent, but interventionist, you begin to realize you've never seen the world as it is, only as it becomes in response to you. In classical physics, reality is assumed to be independent of the observer. The moon is in the sky, whether or not you glance up to see it. A tree falls in the forest and makes a sound, regardless of whether anyone is listening. But the quantum world rebels against that certainty. In it, particles exist not as fixed entities, but as a field of probabilities. They occupy multiple states at once, until observed. Then, and only then, does the particle choose a state, collapsing from superposition into a measurable result. The experiment that revealed this, the famous double-slit experiment, is one of the most elegant and disturbing in all of science. Fire particles, one at a time, at a barrier with two slits, and you get an interference pattern on the screen behind, a signature of wave-like behavior. It's as if the particle went through both slits at once. But install a detector to observe which slit the particle passes through, and the interference vanishes. The pattern changes. The particle decides to go through one slit. The wave collapses into a dot. The act of observing, not touching, not disturbing, merely knowing, alters the outcome. This is not theoretical. This is repeatable, measurable, and deeply unsettling. The particle seems to behave differently based on whether or not someone is watching, as if the universe is reluctant to define itself until you ask, as if the answer only exists once the question is posed. But if matter itself waits for your observation to make a decision, what does that say about the rest of your life? About your relationships, your fears, your memories? Think of the times you've watched someone across a crowded room and seen them transform under your gaze. The way a friend speaks more carefully when they know you're listening. The way your own posture shifts when you catch your reflection. Observation is not neutral. It is catalytic, and you feel it in your bones. You've walked into rooms where you were watched and felt your skin bristle with hyper-awareness. You've been in conversations where the act of being seen made you more articulate or more performative. This is not psychology alone. This is physics leaking into the soul. Because you're not just changing your behavior when observed, you're participating in a loop that changes what's real. That version of you under scrutiny is not the same as the one in solitude. Just like the particle, you collapse into a specific self the moment attention is applied. And this collapse is not a distortion. It is your most real state in that moment. The observer calls forth the observed. The mirror doesn't just reflect. It generates. Now consider this on the level of memory. When you recall a moment from your past, you don't retrieve it like a file. You recreate it. You reconstruct it through the lens of who you are now, from the vantage point of your present awareness. Neuroscience shows us that memories are not stable. They are rewritten each time they're recalled. But what if that's more than a brain quirk? What if it's a manifestation of the observer effect in consciousness? Each time you revisit a memory, you're not just re-experiencing it, you're changing it, reformatting it. The past does not lie dormant. It flutters in a state of quantum ambiguity until you observe it again and lock it into new form. You are the observer collapsing your own timeline into narrative coherence. You are not just living your story, you are authoring its previous chapters in real time. And this isn't just about nostalgia, it's about trauma, about healing, about meaning. Because it suggests that nothing in your past is unchangeable, that every event, every regret, every wound still pulses in a state of interpretive fluidity, waiting for the next act of observation to define its meaning. You don't need to rewrite the facts. You only need to look at them differently. And in that shift, everything changes. This realization also reconfigures how we view others. When you observe someone, not casually but deeply, you affect who they become. Attention is a form of energy transfer. It tells the observed, I see you, and in seeing, I confirm your existence. The gaze stabilizes reality, but it also narrows it. To look at someone is to reduce their possibilities, to nudge them toward one of their many potential selves. This is why we're drawn to those who see us with kindness, because their observation collapses us into a version of ourselves we want to become. And this is why surveillance, even when passive, is oppressive, because it collapses the observed into caricature, into something less fluid, less free. The eye shapes the object. The watcher changes the watched. And if this feels poetic, remember, it is also physics. At the quantum level, the measuring device is part of the system. There is no outside, no objectivity, no clean separation between the observer and the experiment. The same is true in life. You are never uninvolved. You are never merely witnessing. You are always, inevitably, participating. So what does it mean to live ethically in such a world? A world where every glance is a force, every thought a nudge, every belief a sculptor's tool. It means taking responsibility for your perceptions, for the way you look at the world, for the reality you help construct. Because you are not just observing culture, you are co-authoring it. You are not just witnessing suffering. You are either collapsing it into permanence or shifting it into something else through your response. And this is both terrifying and liberating. Terrifying because it means you're never off the hook. Liberating because it means you are never powerless. Your gaze is not passive. It is an act of creation. And if you direct it with care, with compassion, with curiosity, with reverence, you can shape the world not as it is, but as it longs to become. You can collapse it into kindness, into connection, into coherence. And yet we are trained to think of truth as something we uncover, as if the world lies out there, waiting to be found, and our job is to remove the layers of distortion and finally see it for what it is. But maybe truth doesn't pre-exist our awareness. Maybe it crystallizes under the heat of our attention, like frost forming on glass. Maybe we do not find truth. Maybe we birth it. Each act of observation, a kind of midwifery. Each question not a request for information, but a lever that rearranges the answer itself. And this isn't to say that reality is illusion or that facts are fiction. It's to say that reality is participatory, that knowledge is relational, that even the hardest edges of the world are softened by the brush of our consciousness. And once you accept that, you begin to move differently. You look more gently, you listen more deeply, because you know that the very act of doing so is transformative, not just for what you observe, but for who you become. So next time you think you're simply watching, pausing, assessing, analyzing, remember the mirrors, remember the particles, remember that nothing you see is untouched by your seeing, that your awareness is not an idle spectator, but an instrument of reality. You are the ripple in the pond that starts the waves. You are the question that rewrites the past. You are the observer collapsing ambiguity into meaning. And every moment you pay attention, you leave a mark, not just on what is seen, but on the unseen field from which all things emerge. The world, then, is not a stage set before your arrival. It is a script that adapts to your gaze, a story still being written every time you open your eyes. And maybe, just maybe, the most radical thing you can do in a world like this is to look with love. Quantum entanglement. Particles are linked across the universe. Suppose you and another person each hold half of an ancient shattered mirror, two jagged pieces that once belonged to the same whole. You walk away in opposite directions, unaware that the reflections within each shard remain mysteriously connected. One day, As you tilt your fragment ever so slightly, the angle of light changes not only on your side, but, impossibly, on theirs, miles away. Not through signal, not through space, not even through time, but instantly, silently, as if the glass still believes it is unbroken. That's the essence of quantum entanglement, one of the most baffling and beautiful features of our universe. It tells us that particles once joined remain linked forever, no matter how far they drift apart. Not metaphorically, not poetically, but physically, at a level so deep it defies our language. When one of these entangled particles changes state, the other does too, immediately, across vast distances, faster than the speed of light, as if distance were irrelevant, as if space itself were an illusion, as if the universe had no local parts, but only relationships echoing through an invisible web of connection. This is not a metaphorical suggestion. This is the cold, crisp reality of quantum physics. And yet, what it implies is warmer, more intimate, more human than we were ever taught to expect. That separation may be an illusion, that distance may be negotiable, that perhaps everything, everyone, is entangled at a level we are only just beginning to glimpse. Entanglement begins innocently enough. Two particles interact, they collide, or are created in a shared event, and they become entangled, meaning their states are no longer independent. Measure one, and the other's state is instantly known. But it's more than just information sharing. It's not that one particle tells the other what to do. It's that both particles are expressions of the same deeper reality, the same joint state. To speak of them as separate is already to lie. Einstein, troubled by this, famously called it spooky action at a distance, because it seemed to violate the speed limit of the cosmos, the sacred law that nothing can travel faster than light. And yet, time and again, entangled particles behaved in lockstep, their outcomes correlated in ways no classical signal could explain. Experiments by Bell, Aspect, and others confirmed what Einstein resisted. The universe is not built from independent objects, but from interwoven patterns, holistic configurations, entangled states that defy locality. In other words, the universe does not consist of things in space. It consists of space-spanning relationships, like spiderwebs stretching across eternity, vibrating together without regard for distance. And here's the truly radical part. This entanglement does not fade. With separation, you can send one particle to the other side of the Earth, or the galaxy, and their connection remains intact. Entanglement is not like a thread that stretches and thins with distance. It's more like two ends of a dimension you don't understand, where proximity isn't about closeness, but about correlation. Space, as you know it, is background noise to their bond. The measurement of one instantaneously determines the outcome of the other, not through signal, but through a kind of shared being. This violates every instinct we have about how the world should work. We think in terms of cause and effect, in terms of here and there. But quantum mechanics laughs at those distinctions. It suggests a universe where parts are illusions, where the whole is primary, and where what happens to one piece is inseparable from what happens to another, regardless of space, regardless of time. And if that sounds philosophical, it should, because quantum entanglement doesn't just challenge our physics, it challenges our ontology. It challenges what it means to be separate, to be individual, to be alone. Let's pull this into your world. Imagine your emotions entangled with another's across distance. You think of someone you haven't spoken to in years, and a moment later, they call. Coincidence? Maybe. But what if your thoughts, your choices, your inner world are not sealed inside your skull, but radiate into a shared field? What if consciousness itself is entangled? Some physicists speculate that entanglement is the basis of space-time itself, that the geometry of reality arises from patterns of quantum connection. If true, then the separation you feel from others is not fundamental. It's constructed, an illusion born of perspective. And if so, then love, empathy, grief, these aren't just feelings, they're evidence. Evidence that our boundaries are porous, that our being extends beyond our bodies, that we resonate with others, not metaphorically, but literally, at the deepest levels of physical law. You are not a closed system. You are an open node in a cosmic lattice. Your choices, your observations, your feelings, they ripple outward in ways no eye can see. And the same is true of everyone you've ever touched. We are not alone. We are entangled. And this raises a difficult, profound question. If your actions affect others in ways you cannot perceive, what responsibility do you carry? If your internal state is entangled with the world's unfolding, how carefully must you tend to it? The observer effect showed us that watching changes what is seen. Entanglement shows us that being is already shared. So what kind of world are you collapsing into being through your attention, your presence, your pain? We spend our lives trying to protect our independence, to fortify the walls between self and other. But entanglement offers a counter-truth, that your fate is tied to others. That isolation is a fiction. That every decision you make participates in the state of a larger whole. And this isn't a soft, poetic gesture. It's a hard, mathematical claim. The universe is built from entanglement. Reality itself may be emergent from these correlations. There is no fundamental thing, only relationships. The basic unit of reality is not a particle, but a connection. This is not just physics. It is a revolution in worldview. Entanglement asks us to abandon the myth of separateness, not just between particles, but between people, between moments, between intentions and consequences. It suggests that when you suffer, someone else trembles. That when you hope, the universe brightens, not metaphorically, but in measurable, entangled states. And perhaps this is why we cry in movies, why we flinch at the pain of strangers, why we feel when a loved one enters the room without seeing them, because the threads that link us are not imaginary. They are quantum. We are haunted not by ghosts, but by the physics of connection. And the more you open to this possibility, the more the world changes shape. You stop seeing objects and start seeing patterns. You stop seeking control and start seeking coherence. You begin to listen for the harmony between things instead of the boundaries that separate them. But how far does this go? Could the entire universe be one grand entangled system? Could the Big Bang have birthed not billions of particles, but one universal wave function, entangled across all of space and time? In that view, you are not a being in the universe. You are the universe, experiencing itself through a particular lens. Your memories, your choices, your relationships, these are not isolated data points. They are coordinates in a web that spans stars. And this leads to an unsettling possibility, that there may be no randomness, only correlation, that your thoughts are connected to others in ways deeper than language, that your perception is not confined to your eyes, that intuition, coincidence, synchronicity, these are not quirks. They are glimpses of the entangled whole. So what do you do with this? How do you live in a world where everything is connected at a level beyond comprehension? You begin by looking, again, at the ones around you, not as separate minds, but as shared participants in a dance too complex to map. You begin to treat your words, your moods, your attention not as private acts, but as vibrations sent down an infinite string. You stop asking, is this mine or theirs? And start asking, what are we creating together? Because in an entangled universe, you don't get to act alone. Every gesture is a duet. Every thought is a chord. Every breath is an echo. And when you see this, truly see it, something inside you shifts. The loneliness begins to crack. The silence begins to hum. And you realize that the world has always been whispering. You are not alone. You were never alone. You couldn't be alone even if you tried. A particle can take every path until it's observed. Imagine you're standing at a grand crossroads at midnight, surrounded by countless roads, each stretching into a different possibility. Foggy mountain passes, sunlit highways, ancient forest trails, crumbling city streets, and even invisible paths that twist upward into the stars. You haven't moved yet, but somehow you've taken them all. In a way that defies common sense, you've walked every trail, arrived at every destination, lived every outcome. But then, just as you take your first real step, a light flicks on above you. A camera clicks, observation arrives, and in that moment, the illusion vanishes. The other paths collapse into silence, and only one road remains beneath your feet, the one that now seems inevitable. This is not a metaphor for life. This is quantum reality. At the smallest scales, particles do not travel a single tidy path from point A to point B. Instead, they explore every possible route simultaneously in a kind of shimmering super-reality that unfolds beyond space and time. Richard Feynman, one of the pioneers of quantum theory, introduced the path integral formulation of quantum mechanics to describe this bewildering behavior. According to it, a quantum particle like an electron doesn't choose a single trajectory. It samples all trajectories, even absurd ones, like circling the galaxy before arriving at its destination. Every path contributes to the particle's final state, like a grand cosmic orchestra of probability, until a measurement, the act of observation, collapses the symphony into a single note. But what does it mean to say that a particle takes every path? It isn't poetry, it's math. In quantum mechanics, the probability of finding a particle in a particular state is calculated by summing over all possible paths it could take to get there. These paths don't merely represent our ignorance about the particle's motion. They represent real calculable contributions to its behavior. In classical physics, if you throw a baseball, it follows a predictable arc based on gravity and momentum. But if you were to throw a quantum baseball, a subatomic particle, it would travel not just the arc, but every conceivable arc at once. It would roll across the floor, loop around the moon, and dive through the Earth, all in one breathless quantum blur. And yet, we never see such chaos. When we measure the particle, when we force it to reveal itself, it offers us only one answer. Only one path survives the gaze. And so the others disappear, not like discarded options, but like shadows that were never meant to be touched by light. This concept cuts into the heart of how we define reality. In our daily lives, we're trained to think in binaries. A thing either happens or it doesn't. A road is either taken or not. A decision is either made or left behind. But quantum physics suggests a deeper, stranger truth. That possibility is not erased by indecision, but kept alive by it. That, until we look, reality itself is a cloud of potential, waiting to crystallize. This is not some abstract philosophical stance. It's borne out by decades of experimental evidence, from the double-slit experiment to quantum interference, patterns. When particles are not measured, they interfere with themselves, as if they really are taking multiple paths. But once you check, once you peek behind the curtain, that interference vanishes. The particle chooses, or rather, the universe chooses for it. And what's even more mysterious is that your act of observation is what forces that choice. Not the measuring device, not the lab. You. Consciousness, in some interpretations, becomes a participant in reality itself, collapsing the wave function, carving out one path from the sea of maybe. This has implications far beyond physics. Think of your own life. How many paths have you imagined? Careers not taken, words not spoken, cities never visited, people you almost loved. In the quantum realm, the particle gets to try all of them, simultaneously. But in your world, you get one timeline, one unfolding. And yet, the resemblance lingers. Perhaps possibility never truly dies. Perhaps the unseen choices still hum beneath the surface of what is. There is a lesson in that, not just about nature, but about awareness. Before you decide, the world is fluid. After you look, it congeals. So what is the cost of attention? What do you erase by choosing to see? Could your gaze itself be an instrument of creation, and destruction? Could every observation you make be a quiet act of cosmic editing, trimming the multiverse into a single palatable thread? Let's return to the metaphor, the crossroads. When you stand there before observation, you are everything. You are the dreamer and the dream, the walker and the watcher. But the moment you choose, the other versions of you, the ones that took different roads, slip away. And yet, quantum mechanics suggests that in some interpretations, like the many worlds theory, those versions don't vanish. They simply diverge, split off, continue on in universes parallel to yours, where the particle took a different path and you made a different choice. That may sound like science fiction, but it's an interpretation built to preserve the totality of quantum paths. If so, then every decision you make isn't the closure of possibility. It's the birth of new worlds. Every step forward is a kind of branching, a ripple in an infinite field of becoming. The quantum particle teaches us that even when we choose, we are still part of the whole, of everything that might have been. Still, in our observed universe, we only see one path. The others do not show up in our equations. They vanish, or hide, or live on in dimensions we cannot reach. But their influence is not lost. They shape the probabilities. They create interference. They are, in a sense, ghosts, real but unseeable. And perhaps our lives are shaped by similar ghosts. The shadow of the person you could have become haunts your footsteps. The echo of the love you never pursued lingers in your chest. The memory of a decision never made shapes how you make the next one. We are, all of us, shaped by what didn't happen. And maybe that's not a flaw in reality. Maybe it's a feature. Maybe quantum mechanics doesn't just allow for multiple paths. It requires them in order for any single one to exist. Like a painting where every brushstroke matters, even those you cover up. Like music, where the silent notes give meaning to the ones you hear. What doesn't happen is as crucial as what does. And yet, with all this mind-bending beauty, one question remains. What does it mean to observe? Is it merely the act of recording, or something deeper? Does the universe care whether a machine sees a particle, or does it require consciousness? Some interpretations say no, others whisper yes. But either way, it is the act of narrowing that changes things. Observation collapses, attention selects. And in doing so, it changes the story. Perhaps this is the ultimate power of awareness, not just to witness reality, but to sculpt it. Not to uncover what is, but to help determine it. The quantum particle, in its pre-observed state, holds the lesson. The world is not fixed, not solid, not singular. It is a canvas of possibilities, and your gaze is the brush. So the next time you hesitate at a decision, remember the particle. Remember that it once moved in all directions at once. Remember that it never stopped until it was seen. And ask yourself, what might still be possible if you dared to not look too soon? Superposition. Things exist in all states at once. Picture a violin string suspended in absolute stillness, hovering in a void where time hasn't yet chosen a direction and silence holds its breath. And yet somehow, it vibrates with every note it could ever play. A symphony of futures resides in its potential, but none have been heard, none yet chosen. It exists in a state of haunting contradiction, perfectly quiet and infinitely loud. That is the paradox of superposition, the idea that a particle, a thing, a moment, a state of being, can simultaneously exist in multiple realities, not as a blur between them, but as all of them at once, until something, someone, dares to look. Before the gaze, the world is a superposition of everything it could be. Yes and no, light and dark, awake and dreaming. A coin in midair is not heads or tails. It is both, spinning, uncommitted, timeless. In quantum mechanics, this isn't just metaphor, it's the governing rule. At the microscopic level, electrons, photons, even entire molecules can occupy more than one state, more than one location, spin, energy level, path, identity, simultaneously. They exist as a wave of probabilities, a smeared-out canvas of maybes, and it's only upon measurement, observation, awareness, call it what you will, that the wave function collapses and the system chooses a definite outcome. But the act of collapsing is not merely a resolution, it is a sacrifice. To exist in one form, the others must die. Superposition is not a failure of understanding. It is a failure of classical intuition. In the macroscopic world we inhabit, the world of stones, planets, trees, and chairs, things seem to have a single identity. Your coffee cup does not both exist and not exist on the table. Your cat is either sleeping or awake. And yet, in the quantum world, the very act of having only one reality is the anomaly. Schrödinger's cat, that infamous, misunderstood feline, was never meant to be a riddle for children. It was a philosophical scream wrapped in absurdity. The cat, sealed in a box with a quantum mechanism that could trigger poison, is both dead and alive, not in a metaphorical sense, but in the genuine physics of superposition. Until the box is opened, the quantum system inside doesn't decide. It continues to occupy both possibilities, both narratives, both fates. This isn't a flaw. This is the rulebook. Our problem is that we live outside the box and demand the cat pick a side. But what if the universe itself doesn't share our urgency for certainty? Superposition implies that reality is not a line but a cloud, not a point but a field. Every particle, every entity exists as a range of overlapping possibilities, each with its own amplitude, each with its own voice in the final harmony we call now. This principle lies at the heart of quantum computing, where bits are no longer limited to 0 or 1, but can be both, creating a parallelism so vast it threatens to rewrite what we think is computable. But beyond the laboratory, beyond the equations, superposition teaches us something deeply uncomfortable about the nature of existence, that clarity may be an illusion created by ignorance, that the world is not singular until it is forced to be, and that perhaps we too are not as singular as we believe. Have you ever felt torn between two decisions, as though both versions of yourself, the one who stays and the one who leaves, the one who speaks up and the one who stays silent, were real? In the world we inhabit, we're told to choose, to collapse, to be one thing. But what if the multitudes within you are all real, all humming in your psyche like unresolved quantum states? What if the process of living is not about choosing a single self, but collapsing into one version, moment by moment, knowing that others still ripple through the echo chamber of what might have been? Superposition is not just a physical condition, it is an existential condition. You are a symphony of selves, each possible, each valid, each waiting to be observed. And the tragedy, or perhaps the beauty, is that to become one, you must silence the others. In the physical world, superposition is fragile. Interactions with the environment, what physicists call decoherence, destroy it. The moment a quantum system is touched, bumped, illuminated, its delicate balance shatters. The particle falls into place. The note is played. And yet, until that interference, it holds a paradoxical power. It is more than real. It is everything real could be. In that light, one could argue that silence is more than the absence of sound. It is the superposition of all music not yet played. That a blank canvas is more than emptiness. It is the potential for all images. That a human life, unlived, is not nothing, but everything. Until the brush touches the canvas, until the note is struck, until the measurement is made, the universe itself remains an unresolved chord. There's a humility in accepting superposition, a surrender of the ego's need for answers. We like certainty. We crave definition. We want to point and say, that is the truth. But quantum physics replies, truth is the distribution. Reality is the amplitude. Existence is the possibility. And that unsettling whisper has implications, not just for physics, but for meaning, for morality, for identity. Can we really condemn or praise what collapses, knowing it emerged from a sea of might-have-beens? Are our actions definitive, or merely the visible outcome of invisible quantum options? Is there a better version of you in superposition right now? Kinder, braver, more honest? And if so, what would it take to become them? Is it awareness? Is it risk? Is it observation? In a strange way, superposition is the most compassionate theory in physics. It says, you are not defined by your last choice. You are not reduced to one version. You are many things. You are many truths. And only context, only the observer, only the moment, decides which one takes form. This is terrifying, of course. It means we are not fixed, that our identity is less a sculpture and more a wave. But it is also freeing, because it means that change is real, that at every moment, the universe carries with it not just what is, but what could be, and that perhaps the most real thing about you is the trembling uncertainty of who you might become. So next time you stand at a crossroads, emotional, spiritual, existential, remember the violin string, remember the cat in the box, remember the particle that dances in all places, in all spins, in all states, until someone dares to look. And maybe, in those moments of uncertainty, don't rush to collapse. Stay open. Stay indeterminate. Let the wave hum. Let the music build. You are more than one path. You are the whole field. And maybe, just maybe, the most powerful thing you can do is wait before you choose which note to play. You can't know a particle's speed and location at the same time. Imagine trying to capture a lightning bolt in your hands. Not its image, not its echo, but the precise dance of energy that streaks across the sky and vanishes before your thoughts. Can even name it, and just when you think you've caught it, it slips through your fingers because you looked too closely, because your grip insisted on knowing both where it is and where it's going, when the universe never promised to give you both. This is the ghostly tension at the heart of the uncertainty principle, a rule of quantum reality that feels more like a koan than a law of physics. According to Heisenberg, at the smallest scales of existence, nature refuses to reveal everything at once. The more precisely you know a particle's position, its place in space, the less precisely you can know its momentum, its movement, its intent, its direction, and vice versa. It's not a flaw in your instruments or a gap in your knowledge. It's not about better lenses, faster sensors, sharper minds. It is the fabric of reality itself, pulling back the curtain just enough to taunt you with the idea of certainty before vanishing again into probability. In a universe built on quantum rules, there is no hidden blueprint that explains all things. There are only shifting shadows that become sharper when you stop looking for the others. The uncertainty principle is not a statement about measurement. It is a statement about what is. To grasp this is to feel the ground shift beneath the entire scientific method. For centuries, science chased the dream of determinism, that if you knew the initial conditions well enough and the laws that governed them, you could predict the future with flawless precision. Like billiard balls on a table, the world seemed to be a machine, each cause birthing an effect, each motion unfolding like clockwork. Newton gave us that model, and for a time, it worked spectacularly. But at the quantum scale, the machinery collapses. The metaphor of gears and levers disintegrates. Here, particles don't obey. They suggest. They don't follow. They offer possibilities. And Heisenberg's principle is the wall you crash into when you try to bring classical expectations into a quantum realm. You want to know where a particle is and where it's headed. The universe answers, choose one. You cannot have both, because the very act of knowing one alters the landscape of the other. The wave function, that strange mathematical ghost that describes all possible states of a system, spreads out like a whisper until observed. And the moment you touch it, the moment you seek certainty, the probabilities collapse, and with them, the doors to every other version of what might have been. This uncertainty isn't just mathematical, it's existential. It mirrors the contradictions in how we live, how we think, how we love. Have you never tried to pin down your purpose, only to feel your passion slip away as soon as you forced it into a plan? Have you never tried to understand someone you love too deeply, only to find the mystery that drew you to them dissolve under the microscope? To observe too much is to disturb. To demand clarity is to forfeit complexity. The human desire for control, for precision, for exactitude. These are powerful instincts, born from a world that rewards mastery. But in the quantum world, and perhaps in the emotional and philosophical worlds we inhabit too, certainty is a mirage. The more we insist on knowing everything, the less we can truly grasp. Heisenberg's principle teaches that knowledge has a cost, not in money or time, but in sacrifice. Every truth you gain comes with a truth you lose. In physics, that trade-off is built into the equations. In life, it plays out in subtler ways. The more you define your identity, I am this, not that, the more potential selves you must abandon. The more you lock into a path, the more you close the door to all the others. The more you dissect your memories, the more they reshape themselves under scrutiny. The past, like the particle's position, solidifies only when you fix it with your gaze. Until then, it is a cloud of interpretations, drifting. The uncertainty principle may describe subatomic particles, but it echoes in every moment we try to define ourselves too tightly, too completely. We become blurry when pursued too closely, even to ourselves. And yet, uncertainty is not chaos. It is a different kind of order, a deeper, humbler one. It suggests that reality is not made of things, but of relationships. Not of solid particles, but of shifting probabilities that become what they are through interaction, through observation, through participation. We are not passive observers standing apart from the world. We are participants whose questions shape the answers. At the quantum level, the observer cannot be removed. And maybe that's true at the human level too. Maybe how you look at someone changes who they become. Maybe how you frame a question shapes the truth you find. Maybe the world is not out there, waiting to be captured, but in here, unfolding as you engage it. This realization, that knowledge is inherently limited, should feel like a defeat. But strangely, it feels like an invitation. If certainty is unreachable, then wonder becomes the default. If the world will never fully reveal itself, then mystery is not a failure of perception, but a feature of the design. The uncertainty principle doesn't say you can't know. It says you can't know everything at once, and in that crack, possibility blooms. It suggests a reality that is richer than facts, a life that is more than measurement. It says you are not here to master the universe, but to dance with it, to navigate it not like an architect imposing structure, but like a musician improvising within a key, aware that every note chosen means another not played. So when you next feel the ache of not knowing, of not being able to pin something or someone down, remember the lightning. Remember that trying to grasp it destroys its shape, that trying to hold too tightly collapses the dance, that some truths glow brightest when glimpsed from the edge, when respected from a distance, and that sometimes the most honest thing you can say is, I don't know both. I can know one. I can sense its motion, or I can know its place, but never both. Not because I am weak, not because I failed, but because the universe itself insists on that limitation. And maybe, just maybe, that limitation is the most truthful kind of freedom there is. The observer creates the outcome in quantum systems. Think of a mirror in the middle of a forest, one that reflects not what is, but what you expect to see, shaped not by light, but by attention, not by angles, but by intention. And the moment you peer into it, the landscape changes, not just your perception of it, but the very arrangement of trees, the color of the sky, the curvature of the earth itself bends to the gaze. This is not a metaphor for magic, but for quantum mechanics. In this strange realm of the infinitesimally small, particles do not behave like tiny marbles waiting to be found. They exist as clouds of possibility, as probabilities smeared across time and space until someone looks, and then, Like a breath drawn too sharply, reality collapses into a specific form. This is not an act of passive witnessing, it is participation. Observation, in the quantum world, is not the act of opening your eyes to what was always there. It is the act of choosing, collapsing, cutting through the infinite tapestry of potential, futures, and saying, this one. Before the observer, reality is not undecided, it is undefined, and that shifts everything we think we know, not just about science, but about what it means to be. In the classical world, things exist whether or not we see them. A tree falls in a forest, and physics says it still makes a sound. But in quantum mechanics, the question is more delicate. What is the tree before it's observed? A photon is not a particle traveling through space. It is a wave function, an equation, a mathematical ghost that represents every possible place it could be. When you do not look, it is in many places, many states. When you measure it, the wave function collapses. It is no longer a could be, but it is here. The mere act of measuring strips the universe of ambiguity. It's not that reality hides behind a veil and reveals itself when you knock. It's that the veil is all there is until you reach out. The observer is not a detective uncovering clues. The observer is a creator, summoning facts from fiction, substance from shadow. What's astonishing is not that this happens occasionally, but that it's foundational. It's how reality itself works at its core. Take the classic double-slit experiment. Fire electrons through a barrier with two openings, and they act like waves, interfering with themselves, creating patterns on a screen like ripples on a pond. But place a detector at the slits to see which path each electron takes, and the interference vanishes. The electrons behave like particles. Just asking the question, which slit did it go through, forces the universe to answer with a single path. The act of observing doesn't just record what happens, it changes what happens. The observer alters the observed, and not gently. Reality rearranges itself in response to curiosity. This is not some fringe idea. It has been tested, verified, measured, and remeasured in labs around the world. Quantum systems do not resolve into definite states until they are observed. Until then, they are clouds of maybe, dreams of existence. And yet this principle does not stop at particles. It echoes into the realm of consciousness. If the act of observing shapes what is, then what does that mean for us, the ultimate observers of our own experience? Are we shaping not just the quantum foam, but the structure of our own narratives, our identities, our memories? Every time you recall a moment from your past, your brain doesn't retrieve a file. It reconstructs the memory, reshaping it with each retelling. Observation modifies the past. Neuroscience and quantum theory whisper the same uncomfortable truth. Awareness is not passive. It is active, creative, possibly even directive. The more we understand the brain, the more we see that consciousness is not a spotlight that reveals the stage. It is the playwright, writing the script as it shines. This blurring of boundaries between seer and seen raises questions that border on the theological. If the observer creates outcomes, then where is the line between object and subject? Are we distinct from the world we measure, or woven into its very threads? In a quantum system, no event has occurred until it has been observed. But what constitutes an observer? Is it a conscious mind, a camera, a photon bouncing off an eye? Some interpretations of quantum mechanics, like the von Neumann-Wigner hypothesis, flirt with the idea that human consciousness itself is required to collapse the wave function. Others propose that any irreversible interaction does the job. And, yet, the mystery remains. Before interaction, particles are not simply waiting to be revealed. They are undefined. Observation doesn't uncover reality, it defines it. This principle breaks the idea of a pre-written universe. It says the cosmos is not a finished book we're leafing through, but a blank page that responds to the reader's glance. It means we are not just products of the universe. We are participants in its unfolding. The observer becomes a co-author of the script. In the lab, this is measurable. In life, it is poetic. You shape your relationships by how you perceive them. You mold your future by what you believe about it. You become who you are in response to the questions you dare to ask yourself. Just as the quantum world responds to measurement, your identity responds to awareness. What you name becomes real. What you ignore remains in potential. To observe is to choose what becomes real. And that choice, conscious or not, is power. But this power comes with responsibility. If the observer affects the outcome, then the way you look at others can shape who they become. Treat someone as capable, and they rise. Treat them as untrustworthy, and they shrink into that space. The gaze is not neutral, it is a force. Every glance, every interpretation, every framing carries weight. You are not a camera recording what is. You are a mirror, a magnet, a sculptor. The world reflects back the questions you ask it. If you ask, "Why is everything broken?" you will find endless cracks. If you ask, "What can be built?" the universe opens doors you didn't know existed. The observer effect is not just physics, it is philosophy. It is psychology. It is your everyday existence disguised in quantum clothing. And so we find ourselves staring into the mirror again, not the one in the forest, but the one inside. The mirror that shows not your face, but your focus. Not your features, but your framing. The one that doesn't just reflect your reality, it shapes it. The quantum world is not otherworldly. It is this world, stripped of its assumptions. It is the world beneath the world, whispering that nothing is fixed until it is noticed. That possibilities remain open until attention arrives. That you, merely, by looking, are bending the fabric of what is. And if that doesn't make you pause, if that doesn't place awe in the center of your being, then you haven't truly looked yet. Particles have no set properties until measured. Imagine walking into a room where every object only becomes real once you notice it. A chair that remains undefined until you intend to sit. A lamp that only gains shape when you reach to switch it on. Walls that are not solid but spectral until your presence makes them so. And every step you take is not through a pre-existing space, but through a landscape actively woven by your awareness. This is not the premise of a surreal dream, but a reflection of one of quantum physics' most unsettling truths. That particles, the very building blocks of reality, have no definite properties until they are measured. They do not possess a fixed position, a precise momentum, or even a decided spin until the act of observation collapses their wave of possibilities into a concrete outcome. Before that point, they are not here or there, fast or slow, up or down. They are, in the deepest sense, undefined. They exist in a haze of potentialities, a probabilistic fog where countless versions of themselves coexist in superimposed ambiguity, awaiting the moment when a question is asked, a measurement made, and nature commits to an answer. The particle does not travel a single path through the universe. It explores them all until it is forced to choose. And it is this very act of measurement, of peering into the quantum mist, that precipitates reality into being. This idea that the properties of particles do not pre-exist their measurement violates the most basic intuitions we carry about the world. We expect the moon to be there whether or not we look at it. We believe that objects possess qualities, mass, speed, color, temperature, that are intrinsic and independent of whether anyone notices them. But quantum mechanics suggests otherwise. It tells us that before a photon's polarization is measured, it does not have a definite polarization. Before an electron's location is checked, it is not anywhere specifically. It is everywhere it could be, in a probabilistic sense. The wave function, a mathematical entity used in quantum mechanics, describes this haze of potential states. It doesn't tell us where a particle is. It tells us where it might be found if we decide to look. And when we do look, that wave function collapses, not gradually, not subtly, but instantaneously, into a single outcome, one location, one state, one version of reality. This isn't just abstract theorizing. It's been tested again and again. In Bell test experiments, physicists have shown that particles that are entangled can instantaneously influence each other's states across vast distances in ways that defy any idea of pre-existing local properties. If particles had set traits prior to being measured, these effects would not be observed, but they are. What we find instead is a world in which outcomes are not revealed, but decided at the moment of observation. The implications are staggering. The universe is not a static machine ticking away behind the scenes. It is an unfolding drama in which each act is written only as it is performed. The properties of matter are not inked into the fabric of existence. They are drawn in real time by the artist's hand the moment the canvas is lifted. And what is this artist? The measurement, the interaction, the inquiry, the moment when a quantum system is forced to answer a question. It does so by adopting one of many possible realities. Until then, it defers, it floats, it dreams in superpositions. Even the spin of a single electron, whether it points up or down, is undefined until it is measured. Prior to that moment, the particle embodies both options simultaneously, existing in a blur that is not indecision, but an inherent feature of quantum behavior. To call it uncertainty is to undersell the strangeness. It is not that we don't know the particle's state. It's that the state does not exist in any singular form until it is brought forth by observation. Reality is not hidden. It is undetermined. This leads to one of the most important philosophical questions in modern physics. Does the act of observation create reality? If the properties of particles are undefined until measured, then in what sense do they exist before we look? Are they merely potentialities, mathematical ghosts waiting to be summoned into form? And if so, what does that mean for the nature of the universe? Are we explorers discovering what is already there, or are we co-creators shaping what comes into being? The quantum world seems to whisper that our questions are not neutral, that every act of inquiry disturbs the balance, changes the outcome, spins the wheel of possibility. To observe is to affect, to measure is to participate. The observer is never detached. They are entangled with the system they examine. In everyday life, we are insulated from these quantum uncertainties by the sheer scale of things. A baseball has a defined position and velocity because it contains trillions upon trillions of quantum particles whose uncertainties average out. But at the fundamental level, where particles blink in and out of existence, where matter is less substance than shadow, the rules are different. There, the universe is less a clockwork machine and more a question still being asked. And perhaps this is not just a fact about physics, but a mirror for our own minds. How often do we assume our identities, our emotions, our decisions are fixed properties? How often do we forget that much of who we are remains undefined until we are challenged, observed, reflected upon? Just as particles crystallize into reality under scrutiny, so too do our values, our priorities, our truths take shape under pressure. You are not just what you are. You are what you become when the moment calls upon you. The quantum world suggests a radical humility. It tells us we cannot speak of what is without acknowledging our role in bringing it forth. It tells us that properties are not fixed, but fluid, that certainty is not a given, but a negotiation between what could be and what is demanded, and it invites us to let go of the illusion that the universe is fully formed, waiting to be surveyed. Instead, it offers a view in which existence is participatory, dynamic, responsive. Measurement is not a window, it is a brushstroke. Observation is not a lens, it is a chisel. The observer is not standing outside the frame, they are inside it, shaping it, living it. And so we return to that room where reality remains blurred, unformed, until you enter. You reach for a switch, and only then does light emerge. You extend a hand, and only then does the object materialize to meet it. Every step you take does not follow a fixed map. It creates the path beneath your feet. Particles, it seems, are not reluctant to be known. They are incomplete until they are. And perhaps so are we. Quantum tunneling. Particles pass through barriers. They shouldn't. What if the walls you thought were impenetrable, the locked doors of fate, the ceilings of possibility, the concrete barriers between where you are and where you long to be, were not as solid as they seemed? Imagine walking toward a towering stone wall, one that has stood for centuries, and realizing that if you do not stop, if you press forward with enough certainty, you might, against all expectation, pass through it. Not around it, not over it, but through it. This is not a metaphor invented for inspiration. It is a principle embedded in the fabric of our universe, whispered by particles too small to see, too elusive to predict. Quantum tunneling is the stunning revelation that, in the realm beneath perception, boundaries are negotiable, and even the laws of classical logic bow to something deeper, stranger, and far more forgiving. In the world of the very small, particles are not bound by the rules we impose on them. They do not always respect the notion that you must have enough energy to climb a hill before reaching the other side. Sometimes, they simply disappear from one side of the barrier and appear on the other, as if the wall they were supposed to bounce off of never existed at all. This is not magic. This is quantum mechanics. At the heart of tunneling is the concept of probability. In classical physics, a ball rolling toward a hill will only make it to the other side if it has enough energy to reach the peak. If it doesn't, it rolls back, defeated by gravity and friction. This is the universe we know, predictable, restrained, grounded in determinism. But quantum mechanics offers another version of reality, one in which particles are not confined to definite paths, but are instead described by wave functions that stretch across space, assigning probabilities to every conceivable location. These waves do not end at barriers, they only decay. And as long as the wave continues to exist, even faintly, on the other side of a barrier, there remains a chance, however small, that the particle can be found there. It doesn't climb over. It doesn't break through. It tunnels. The particle, in some very real sense, stops being a particle at all and becomes a whisper of potentiality, an echo of what could be. And sometimes, the universe answers that echo. This behavior is not just theoretical. It is essential to how our world works. Quantum tunneling enables nuclear fusion inside the sun, where hydrogen atoms overcome repulsive forces to bind together, releasing the light and warmth that sustains life on Earth. Without tunneling, that fusion would never occur, and the stars would remain dark and cold. Tunneling is also the reason why semiconductors and transistors function, the very foundation of the digital age. The device you're reading this on would not exist without the ability of particles to slip through energy barriers they shouldn't cross. And yet, despite its ubiquity, tunneling remains profoundly counterintuitive. It defies our everyday expectations that effort should match result, that force should be met with resistance, that barriers should block what is not strong enough to overcome them. Quantum mechanics rewrites that script. It whispers that the world is not built of walls, but of probabilities, and those probabilities sometimes allow for the impossible to occur. But beyond the mathematics, quantum tunneling invites us to reconsider something deeply human, our relationship with limitation. How often do we treat circumstances as absolute? How often do we accept the verdict of reality too soon, mistaking delay for denial or resistance for finality? We encounter emotional barriers, social walls, psychological ceilings, and we stop. We tell ourselves that progress requires power, that change demands force, that anything worth reaching must be earned with overwhelming energy. But the quantum world suggests a different path, that persistence, presence, and probability can sometimes achieve what brute strength cannot. That existence itself is not a series of fixed outcomes, but a field of fluctuating chances, where even the most impassable boundary may harbor a faint echo of escape. And perhaps this is where metaphor and mechanics meet most intimately. Quantum tunneling does not promise guaranteed outcomes. It offers possibility in the face of improbability. It reminds us that a system doesn't need certainty to change. It needs only a sliver of amplitude, a whisper of potential, a flicker of chance. that refuses to be zero. And that is often enough. In a universe where particles can pass through forbidden regions simply because their presence there is not entirely ruled out, we are invited to wonder, what barriers in our own lives are only as real as our acceptance of them? What walls persist only because we turn back at their edge, never testing whether the world might yield under a more subtle form of movement, not a forceful push, but a quiet persistence? The strange beauty of tunneling is that it preserves a kind of grace. It doesn't smash, it doesn't invade, it doesn't conquer, it permeates. It slides between the cracks of what should be, not to destroy structure, but to reveal that structure was never as absolute as we believed. In this way, quantum tunneling is not just a physical process. It is a philosophical whisper about the malleability of reality. It is a reminder that even laws have loopholes, that even rules leave room for uncertainty, and that within the space between yes and no lies a narrow corridor where miracles happen, not loudly but silently, not through might but through possibility. And yet the implications go even further. If particles can tunnel, then so too can information, influence, even identity. Tunneling challenges the notion of separateness. If a particle is here and then suddenly found there, without crossing the space in between, what does that say about continuity, about presence, about movement itself? It suggests that the fabric of the universe may be less about sequence and more about connection. That the spaces between are not voids, but veils. And behind those veils, everything is entangled in a dance of potentialities, waiting for the right question, the right context, the right moment to become real. So much of our experience is bounded by the illusion of permanence. We build narratives around the walls of who we think we are, what we believe we deserve, and what we believe is possible. We assume that the past is fixed, that the future is far, that the present is solid. But tunneling hints that time, like space, is not a prison, but a palette. That change does not require destruction. It only requires allowance. That presence is not limited by position, and movement is not limited by momentum. The particle does not ask whether it can. It simply exists within a framework where maybe is enough. And perhaps we too can learn to live in the space of maybe. To tunnel is not to deny the wall. It is to recognize that the wall does not own all outcomes. It is to understand that being blocked does not mean being stopped, that encountering resistance is not the same as reaching the end. It is to inhabit possibility with patience, to trust in the unseen mechanisms that may allow passage when logic says none exists. And this is not blind optimism. It is quantum wisdom. It is the mathematics of humility, the physics of faith, the science of the improbable. It is the universe reminding us that no structure is absolute, no limitation eternal, no separation insurmountable. Even in the darkest depths of what should be impossible, the wave function continues, faint, fading, but never extinguished. And that alone is enough for something to pass through. Quantum randomness, not even the universe, knows what happens next. Imagine tossing a coin in a world where even the coin doesn't know which way it will land. Not because it's mid-air, not because of wind, friction, or flawed prediction, but because the very fabric of reality itself hasn't decided yet. Imagine a casino run by the universe, where the roulette wheel spins without rules, the dice fall without weight, and every outcome emerges from a void not of mystery, but of true indeterminacy. This isn't fantasy. It's the bizarre playground of quantum mechanics, where randomness isn't just a gap in human knowledge, but a fundamental property of existence. In the quantum world, events do not unfold according to strict, knowable chains of cause and effect. Instead, they shimmer on the edge of potentiality, waiting not to be determined, but to simply happen. There is no hidden script, no backstage director pulling levers behind particles. What occurs, when, where, and how, is born not from necessity, but from sheer probabilistic spontaneity. The spin of an electron, the decay of a nucleus, the path a photon takes through a crystal, all emerge not because they must, but because they might. And in that tiny space between might and must, our entire understanding of determinism crumbles. For centuries, science sought to tame the universe into a machine, gears grinding in unison, every motion the result of some prior push. Newton's laws gave us a cosmos of consequence, predictable, mechanical, graspable. If you knew everything about a system, you could predict its future with perfect accuracy. The universe, it seemed, was a giant clock, and with enough data, we could wind it forward or backward at will. But quantum mechanics shattered that illusion. In its equations, particularly in the Born rule, which translates the mathematics of wave functions into observable outcomes, we find not certainty, but probability. A particle might appear here or there, spin up or down, decay now or later. Nothing, not even the laws of physics, can say in advance which. This isn't ignorance. It's not that we don't know, it's that the universe itself doesn't know, until the moment happens. And even then, the decision doesn't come from a hidden variable or an unseen cause. It arises from chance, pure and unapologetic. Take radioactive decay, for example. An unstable atom sits quietly, no external disturbance, no change in temperature or pressure, and then, suddenly, it emits a particle, transforming into something new. Why then? Why not earlier? Why not later? There is no answer, no deeper mechanism. The best we can do is assign a half-life, a statistical average. The rest is left to randomness. This isn't a defect of theory, it's a revelation. At its core, quantum randomness tells us that some things just happen. They don't have to. They don't not have to. They just do. And in that simple truth lies one of the most profound philosophical challenges ever faced by science. A universe that is not fully predictable is a universe that is, at least in part, unknowable. Not just to us, but even to itself. Einstein famously resisted this. God does not play dice with the universe, he protested, unable to accept that reality might rest on a foundation of uncertainty. But experiment after experiment, Bell's inequalities, quantum erasers, photon polarizations, confirmed what the math had suggested all along: the dice are real. And they're not just in God's hands. They're built into the architecture of existence. This isn't chaos. It's a different kind of order. One where possibility, not certainty, is the bedrock. Where the future is not written in the past, but co-authored in the instant of becoming. And this randomness is not confined to obscure laboratories or esoteric particles. It reaches into everything. The chemical reactions that drive life, the quantum fluctuations that seeded galaxies, the neurological noise that may underlie free will, all draw from this well of unpredictability. Every breath you take, every thought you form, might be riding on a ripple of quantum chance. It is sobering, even disorienting, to realize that beneath the world of objects and events lies a substrate that resists order. We like to think of the future as a consequence of the past, a sequence, a chain. But quantum mechanics invites us to see it as a garden of forking paths where the route ahead is not chosen but discovered. This has unsettling implications. If even the universe can't predict what happens next, what becomes of causality, of meaning, of control? We often equate randomness with meaninglessness, but that is a bias born of our discomfort with not knowing. In truth, randomness may be the space where creativity lives. It is the crack in the system that allows novelty to emerge. A world of total predictability would be a frozen one. No surprise, no choice, no deviation. But a world with randomness breathes. It adapts, it evolves. Evolution itself is driven by mutation, which at the genetic level arises from quantum-level uncertainties. Consciousness, too, may be flavored by quantum noise, adding a flicker of spontaneity to thought. In this sense, randomness is not the enemy of reason. It is the mother of all that is new. Still, the human mind resists. We crave patterns. We find comfort in cause and effect. Our brains are prediction machines, constantly scanning the future for clues, rehearsing outcomes, calculating risk. But quantum randomness humbles that impulse. It tells us that not everything can be foreseen, not every question can be answered, not every outcome can be controlled. This is not a flaw, it is an invitation to live not in fear of uncertainty, but in relationship with it, to walk not with a map, but with a compass, to act not because the result is guaranteed, but because the act itself is worthwhile. And in this way, quantum randomness becomes a metaphor for human experience. We do not know what will happen when we speak a truth, take a risk, love someone, leave something behind. We cannot. The variables are too many, the interactions too subtle. But still we act. We choose. We step forward into the unknown, hoping that somewhere within the space of possibility, something meaningful will unfold. That is quantum courage, the willingness to leap without knowing where we'll land. Not because we trust in certainty, but because we trust in potential. So what does it mean, ultimately, that the universe contains true randomness? It means that the cosmos is not a machine, but a dance, not a code, but a conversation. It means that within every moment lies not just what is, but what might be. And while we cannot control that randomness, we can learn to live with it, to find grace in uncertainty, to make peace with mystery, to stop demanding that every answer be knowable and start embracing the beauty of not knowing. Because in that space of not knowing, in that flicker before the outcome, life happens, art happens, love happens. And sometimes a particle chooses a path that no law could have predicted, not because it was forced, but because it was free. Quantum erasure. You can erase information after it's recorded. Imagine walking into a vast, ancient library where every book writes itself the moment you read it, yet vanishes if you forget having ever opened it. Imagine memories inked not, in permanence but in possibility, flickering, conditional, and reversible. Now imagine a universe built on that logic, where information isn't an absolute, but a suggestion, where reality isn't merely shaped by what you observe, but also by whether you choose to preserve the record of that observation. This isn't a parable, it's the perplexing truth behind one of quantum physics' most unsettling revelations, quantum erasure. In this strange corner of the quantum world, you can measure a system, learn something real about it, and then, by deleting the context of your observation, undo the consequences as if the measurement never happened. It's as though the universe itself allows you to rewind causality, not by turning back time, but by erasing the meaning of having ever looked. And in doing so, it raises a haunting question. If reality only congeals around the information we choose to keep, what else are we unknowingly letting dissolve? At the heart of quantum erasure is the dual nature of particles, the ability for photons, electrons, and atoms to behave as either particles or waves, depending entirely on how they are observed. This duality lies at the foundation of quantum mechanics, most famously illustrated by the double-slit experiment, where particles fired at a screen through two slits form an interference pattern, like ripples of water overlapping, unless you observe which slit they go through. The moment you measure the path, the pattern collapses. The wave disappears, and the particle acts like a discrete object. This suggested a disturbing truth. Observing a quantum system doesn't just reveal its state, it changes it. But what if you could undo that change? What if you could record the which path information, then later choose to erase that information and watch the wave pattern reappear, as if you had never looked at all? That's the quantum eraser. In these experiments, particles are entangled, linked, in such a way that measuring one immediately affects the other, regardless of the distance between them. Imagine a pair of entangled photons. One heads to a detector that measures its path through a double-slit setup, while the other flies to a distant device that either preserves or erases the which path data. If the path information is kept, the interference pattern vanishes. But if the information is erased, even after the first photon has already hit the detector, the interference returns. The mere act of removing knowledge restores the wave behavior, not just metaphysically, but visibly, measurably, undeniably. Somehow, the universe behaves as if the past is contingent on whether we decide to preserve the memory of it. It doesn't rewrite history. It lets the past exist in a superposed state until we either choose to confirm it or choose to forget. This idea doesn't merely strain logic, it rends the fabric of linear time. Because in quantum erasure, decisions made in the present affect the interpretation of events that have already occurred. The future, in a very real sense, reaches backward and reshapes what was, not by changing the particles themselves, but by altering what we're allowed to know about them. It's not time travel, it's time ambiguity. The particles passed. Reality remains fuzzy until the observer resolves whether the measurement counts. And that decision, even if made after the detection, seems to determine whether the particle behaved like a wave or a point. We are forced to entertain a truth far more radical than we're comfortable with, that observation does not merely collapse a wave function, but perhaps, by erasing it, uncollapses it, revives its ghost, and sets possibility back in motion. This is not a loophole or a trick of data. Quantum erasure has been demonstrated in the lab. Delayed choice quantum eraser experiments, like those devised by Yoon-Ho Kim and colleagues, show this effect with breathtaking clarity. Information is not a passive result of measurement. It is an active agent in the unfolding of reality. And when that information is discarded, the consequences vanish with it. But what is information? Is it the physical imprint of photons on a screen? Is it the electronic states of a detector? Or is it something more abstract, something dependent on whether a conscious observer could, in principle, know the result? These questions bleed into philosophy, into cognitive science, into epistemology. Because if the act of erasure alters what was, what happens when we forget? What happens when no one looks? What if your memories, your perceptions, your understanding of reality all hinge on choices not yet made? The metaphors are dizzying. It's as though we're watching a movie, but the plot only stabilizes when we commit it to memory. Until then, every scene is still in flux, every character uncertain, every twist provisional. The film runs backward and forward at once, collapsing only when we say, yes, this happened. But if we later say, no, I didn't see that, the reel rewinds and plays a different version. Quantum erasure does not suggest that we can change the past. Rather, it tells us the past was never fixed to begin with. It was waiting for us to decide whether to remember. This has profound implications for how we think about causality, agency, and even ethics. In a world where knowing shapes being, where deleting knowledge alters behavior, responsibility itself becomes a spectrum, not a binary. If we know that knowing changes things, are we culpable for choosing ignorance? If we erase the context of a choice, do we also erase its weight? Are our regrets and our reliefs equally subject to quantum contingency? These questions, once confined to theology or existential philosophy, now sprout from the very roots of physics. But perhaps the most intimate implication is psychological. Our brains, too, are information processors. They observe, record, delete. Memories fade. Awareness sharpens or slips. Trauma is buried. Joy is forgotten. Is our personal reality also shaped by quantum-like erasures? Does forgetting allow a new narrative to form? Not because we invent it, but because the old one ceases to exist in the absence of attention. In this light, healing may not be rewriting, but unknowing. Letting the collapse reverse, letting the pattern reappear. And in this lies a paradox both haunting and hopeful. If observation defines reality, and erasure undefines it, then we are both sculptors and erasers of our world. We do not merely walk through a pre-written story. We help write the words, and sometimes we choose to smudge the ink. The universe, it seems, is not a ledger, but a living draft. And you, in your quiet choices of what to remember and what to let go, are part of the editing process. You are both reader and author, both witness and eraser. And the final version of your world may depend not only on what you saw, but on what you chose to forget. Quantum interactions are reversible, but the world isn't. Imagine a pristine lake at sunrise, utterly still, mirroring the sky so perfectly that you cannot tell where water ends and the heavens begin. Then toss a stone into it. Ripples spread outward, the surface dances with waves, and the perfect reflection is lost. Now imagine trying to reverse those ripples, to reclaim that original stillness. You'd need to reach out and collect every molecule, every vibration, every photon of light reflected from the surface, and send them all backward with perfect precision. In theory, under the laws of quantum mechanics, that reversal is possible. The microscopic equations that govern particles are time-symmetric. They don't care whether time flows forward or backward, but the world we live in does. The lake never returns to its perfect calm. The ripples don't unsplash. And therein lies one of the strangest paradoxes at the heart of physics. At the quantum level, the universe is reversible. But our macroscopic world, the world of people, of history, of heartbreak and progress, stubbornly flows in one direction, like a river that never turns back. Why is that? Why do the equations whisper symmetry, but reality screams decay? At the heart of this tension lies the difference between what is mathematically permitted and what is physically probable. Schrödinger's equation, the governing principle of non-relativistic quantum mechanics, is perfectly reversible. If you know the wave function of a system at one moment, you can calculate both its future and its past states with equal precision. The evolution of that wave function is deterministic and unitary, preserving all information, that is, unless it is measured. But even then, interpretations like many worlds preserve reversibility by branching instead of collapsing. On paper, the quantum realm respects time like a mirror. What goes forward can, in principle, go backward. Yet the universe we inhabit doesn't behave that way. Ice cubes melt in warm water, but we never see them reform. Buildings collapse in earthquakes, but we never watch rubble reassemble into walls. Memories accumulate, but they don't erase themselves. This asymmetry, this irreversible march of time, is not written into the laws of quantum mechanics. It emerges when many quantum systems interact, when entanglement spirals into chaos, when entropy takes the reins. Entropy, the measure of disorder, is the great arrow of time. It's why you age, why your coffee cools, why stars burn out and civilizations crumble. Entropy increases because there are more disordered states than ordered ones, and given enough time, systems tend to move from unlikely configurations to more probable ones. It's not that atoms can't return to order, it's just fantastically unlikely that they will. Imagine throwing a deck of cards in the air and having them land perfectly sorted by suit and number. It's not impossible, it's just statistically absurd. The same is true of your body, your mind, your memories, your entire life. Every moment you live is an arrangement of particles more disordered than the moment before. Not because those particles can't reverse, but because they almost never do. This, then, is the crack between quantum reversibility and worldly irreversibility. The divide between what is possible and what is probable. Still, quantum mechanics teases us with reversals. Experiments in weak measurement, quantum teleportation, and Loschmidt echoes allow physicists to undo certain quantum states under highly controlled conditions. Quantum error correction can reverse decoherence. Entangled photons can be manipulated to restore previous states. In these rare and delicate circumstances, it's as if the universe momentarily forgets its forward bias. But these are exceptions that prove the rule. Because the moment those systems interact with a larger environment, with air, with light, with you, the information leaks away and reversibility becomes a ghost. Decoherence, the bleeding of quantum information into the environment, turns quantum purity into classical messiness. What begins as a crisp quantum state becomes a blur of probabilities. The world, with its trillions of particles colliding and vibrating and radiating, quickly drowns any chance of rewind. The arrow of time sharpens not at the level of particles, but in the crowd of their interactions. This realization haunts more than just physicists. It haunts philosophers, theologians, psychologists, because it means that while the core of reality may be reversible, our experience of it is not. You cannot unspeak words once they're heard. You cannot unchoose a path once it's walked. You cannot unhurt someone after the pain has been felt. These are not just social truths. They are thermodynamic ones, the emotional entropy of life, the way relationships unravel, the way trust decays, the way moments become memories, mirrors the physical entropy of the universe. There is no cosmic undo button. And yet, knowing that, we ache for it. We imagine time machines, second chances, clean slates, but the universe offers none. It only offers now, a fleeting present sliding irrevocably into a diffused future. Still, there is a kind of grace in this irreversibility, because it gives meaning to choice. If everything could be undone, then nothing would matter. But the fact that our actions echo forward, that our decisions carve irreversible paths into the fabric of time, gives weight to being. The irreversibility of the world makes life not a loop, but a story, with chapters, with consequences, with endings. And stories, unlike equations, are meant to move in one direction. This is the paradox. The universe is reversible, but its meaning is not. You can't return to who you were before you knew grief, or love, or loss. You can't rewind the clock to unmeet someone, or to unlearn a truth that cracked your worldview open. Those transformations are permanent. They are the soul's entropy. Even at the edge of physics, this lesson holds. Black holes, those enigmatic voids of gravity, were once thought to destroy information. But modern theories suggest that information is preserved in Hawking radiation, in holographic horizons, in entangled pairs. Still, recovering that information is so unfathomably complex that for all practical purposes, it is gone. Reversibility, again, remains a technicality. In life too, we retain traces, photographs, journal entries, scars. But those fragments are not the experience. They are echoes, shadows of states that no longer exist. So what does it mean for you to live in a world built on reversible particles, yet flowing irreversibly toward entropy? It means you are a process, not a snapshot. It means nostalgia is inevitable, but resurrection is not. It means the pain you feel in moments of regret is the cost of being a temporal being. And it means that every present moment is precious precisely because it cannot be repeated. Quantum mechanics may offer a blueprint of reversibility, but the architecture of your life is sculpted by one-way time. And so you must make peace with the ripple you send into the lake, knowing it cannot be unmade. Vacuum fluctuations, space boils with ghost particles. Imagine standing in a vast, silent desert under a moonless sky, believing yourself to be utterly alone, surrounded by nothing but empty air and stillness, until, with no warning, the sand beneath your feet shudders, as if something beneath the surface had stirred, unseen and uninvited. That tremble, that unexpected pulse in a place you thought lifeless, is the closest metaphor we have to what happens in the vacuum of space. Because contrary to everything intuition whispers, the void is not empty. Even in its most absolute silence, the vacuum is alive with motion. It seethes, it fluctuates, it boils, not with heat, but with potential. A roiling, restless foam of ghost particles that flicker into existence and vanish again before time can fully register their birth. These are not poetic fantasies or exaggerated metaphors. These are vacuum fluctuations, real phenomena predicted by quantum field theory and confirmed by experiments so delicate they dance on the edge of invisibility. The idea that nothing is truly nothing has long since been exiled from modern physics. In the quantum world, nothingness is unstable, foaming with spontaneous possibilities, a storm of virtual particles that emerge from nowhere and collapse into nowhere, changing the very fabric of the cosmos with every fleeting breath they take. To understand this, You have to shed every notion of emptiness you've ever carried. The classical idea of a vacuum, a box devoid of matter, a total absence of particles and energy, is obsolete. In quantum field theory, every point in space is pervaded by fields. For electrons, photons, quarks, gluons, and even in the absence of particles, those fields remain. But they are not silent. Because of the Heisenberg uncertainty principle, which tells us that certain properties like energy and time cannot both be known with absolute certainty, even a perfect vacuum cannot have zero energy. That baseline energy, called zero-point energy, ensures that even empty space is not truly at rest. It vibrates, it surges, it flickers. The vacuum is like a pond covered by a perfect sheet of glass, beneath which eels of pure probability twist and coil, breaking the surface only to dive again before you can blink. Virtual particles, particle-antiparticle pairs, appear from the vacuum and annihilate each other within such short time frames that they leave no permanent trace, but their effects can be measured. They influence forces between particles. They shift atomic energy levels. They change the charge of the electron. Their reality is ghostly, yes, but not unreal. This isn't speculation. It's been measured, indirectly, but unmistakably. The famous Casimir effect is the proof. Place two uncharged metal plates a few nanometers apart in a vacuum, and quantum fluctuations between them are restricted compared to outside. The result: a measurable attractive force pushes them together. There's no air, no gravity, no particles, just vacuum energy doing the impossible, creating motion from apparent stillness. Then there's the Lamb shift, an adjustment in the hydrogen atom's energy levels caused by interactions with the vacuum's ephemeral particles, or Hawking radiation, the theoretical prediction that black holes can evaporate because virtual particle pairs near the event horizon can be split, with one falling in and the other escaping. That means black holes, those monuments to gravitational death, may slowly fade, not in silence, but because of the whispering restlessness of the vacuum. This is no passive backdrop to the universe. It is the stage, the actor, and the playwright, all at once. And yet, for all its strange vitality, vacuum fluctuation invites us into an even stranger philosophical territory, the idea that the universe in its entirety could have emerged from nothing. If the vacuum is not truly empty, but a bubbling froth of potential, could our cosmos have been born from a particularly strong fluctuation? This is not idle speculation. Some inflationary models of the early universe propose that a quantum fluctuation in a metastable vacuum, a so-called false vacuum, could have triggered cosmic inflation, expanding a single region of fluctuating nothingness into the vast everything we now inhabit. That would mean the universe has no cause, no creator in the traditional sense, only a random breath in an eternal sea of vacuum potential. From the outside, it's madness. From within physics, it's a viable origin story, a flicker of nothing that became everything. But the implications go even deeper. If the vacuum never rests, then stability is an illusion. Your atoms, your body, your world, they seem solid and unchanging, but they rest atop a sea of seething possibility, like walking across a frozen lake that creaks beneath your every step, held together not by silence, but by dynamic equilibrium. The mass of every particle, the very constants of nature, may be continuously sculpted by the symphony of virtual particles playing beneath the stage of matter. And what's more, these fluctuations do not obey your intuitions about locality or causality. They appear and vanish in ways that make nonsense of classical thinking. They don't follow trajectories, they don't persist. They are the almost real, entities whose existence is permitted by quantum rules, so long as they vanish quickly enough to satisfy energy-time uncertainty. There's something existentially haunting about this, that what we call empty is the most active canvas of all, that beneath your every action, thought or breath, a theatre of quantum chaos dances invisibly, that your perception of stillness, of calm, of silence, is a lie. Not because you're wrong, but because your senses are too slow, too coarse, too anchored in macro reality to hear the whisper of the vacuum's song. But the universe listens. Particles shift, energies curve, black holes whisper, galaxies birth and die, and behind it all, the invisible rhythm of ghost particles plays on. So what does it mean to live in a reality where the emptiest parts are the most alive? It means that mystery is not at the edge of science. It is its heart. It means that the line between existence and non-existence is thin, porous, and constantly crossed. It means that from within the seeming void, change can erupt, information can emerge, and creation can unfold without warning. You were born not on solid ground, but on a quantum foam that never stops seething. And in some deep sense, that means you too are part of the fluctuation, a temporary arrangement of borrowed energy and improbable order, rising, trembling, and one day falling back into the sea of potential from which all things come. Quantum mechanics allows particles to borrow energy temporarily. Imagine you're walking through a city late at night, and every street lamp you pass flickers as you approach. Just enough light to guide your next step, then fading behind you into darkness again. You don't know where the energy comes from, or why it responds to you, only that it does. As if the very laws of motion were being bent for a moment, so you could continue forward. This is the illusion of continuity we live within. And it is also the echo of what happens at the smallest scales of reality. In the quantum world, particles move, exist, and interact in ways that defy everything we believe about cost, debt, and permanence. Because in this strange foundation of the universe, energy can be borrowed, temporarily, fleetingly, as long as it is returned before the universe notices the books are unbalanced. It's a cosmic accounting trick allowed by quantum mechanics, one that permits virtual particles to emerge from nowhere. Lets particles cheat energy conservation for unimaginably short durations, and makes room for phenomena that would be impossible in any classical framework. This isn't just a quirk or loophole. It's one of the defining features of reality, a subtle crack in the logic of existence through which the impossible briefly slips into being, only to vanish again before it can be measured. At the heart of this concept lies the Heisenberg uncertainty principle, not the one about position and momentum, but the equally profound version that ties together energy and time. It tells us that the more precisely you define the energy of a system, the less you can know about how long it maintains that energy, and vice versa. This means that if something exists only for a very short period of time, it can borrow a surprising amount of energy during that fleeting existence, provided it gives it back quickly enough. This is not a violation of conservation laws, but a deeper version of them. Conservation is still true, but in the quantum world, true often comes with asterisks. These momentary borrowings of energy give rise to virtual particles, particle-antiparticle pairs that spontaneously blink into existence in the vacuum, interact briefly with their environment, and annihilate each other before they can be directly observed. Though they are invisible to direct detection, they are not meaningless. They affect real particles, they shift energy levels, they influence electromagnetic fields, they reshape space itself. The universe, it seems, is built not on solid rules, but on elastic tolerances, not on laws, but on allowances. Take, for example, Hawking radiation, the theoretical prediction that black holes, those devourers of matter and energy, are not perfectly sealed coffins of gravity, but slowly leaking through quantum loopholes. Near the event horizon, pairs of virtual particles constantly pop into being. Occasionally, one falls into the black hole while the other escapes, becoming real and radiating into the universe. The black hole loses a tiny bit of mass in the process, as if the universe is letting particles borrow energy from the vacuum and charging the debt to the black hole's account. Over trillions of years, this can lead to the complete evaporation of a black hole, not through violence, but through quiet quantum erosion. This is the power of borrowed energy, not explosive, not loud, but relentless, and written into the fabric of space-time itself. Or consider quantum tunneling, a phenomenon that defies the classical idea that a particle needs enough energy to surmount a barrier. In quantum mechanics, particles can appear on the other side of an energy wall they shouldn't be able to cross, as if they borrowed energy for a blink of time to slip through, repaying it instantly upon arrival. This is how nuclear fusion works. In the Sun, protons overcome electrostatic repulsion, not by force, but by probabilistic sleight of hand. It's how scanning tunneling microscopes map the surfaces of atoms. It's how radioactive decay occurs. The universe, again and again, shows that certainty is not its native language, probability is. And borrowing energy is just one way it whispers, maybe, where classical physics would shout, impossible. But perhaps the strangest part of this quantum borrowing is not its mechanics, but what it says about time and causality. In our everyday experience, debt and repayment happen in sequence. You borrow first, you repay later. But in quantum mechanics, the timing is blurrier. A virtual particle can affect a real one, leave a fingerprint on a process, and then vanish before the interaction is even finished. The cause can dissolve before the effect concludes. The energy can fluctuate before the measurement. In quantum field theory, calculations often involve loop diagrams, where particles interact with themselves via paths that loop backward in time. It's not just about borrowing energy, it's about bending the timeline to accommodate that loan. Time becomes a suggestion, order becomes negotiable, and yet, even within this ambiguity, patterns emerge. The amount of energy that can be borrowed is inversely proportional to the time it's borrowed for. High energy fluctuations must vanish almost instantly. Longer-lived disturbances are gentler. It's a kind of quantum karma. The more you take, the faster you must return it. The rules of the universe bend, but they do not break. They flex, but they do not forget. It's as if reality is a marketplace of probabilities, where every action is allowed a brief overdraw, provided the books balance out before the cosmos audits the account. This metaphorical economy underpins everything from atomic behavior to the evolution of galaxies. And unlike any economy we know, it never defaults. It runs silently, flawlessly, invisibly. A system of temporary chaos that adds up to permanent order. Fascinatingly, this temporary energy also contributes to one of the most puzzling features of modern physics: the cosmological constant problem. When physicists try to calculate the vacuum energy of space, summing up all the possible energy borrowed by all virtual particles across all possible quantum fields, the result is astronomically large, so large it would curve space-time, with crushing force collapsing the universe instantly. But the actual cosmological constant, the one we observe, is small, gentle, just enough to accelerate cosmic expansion without tearing the universe apart. Why the discrepancy? No one knows. The borrowed energy is there. It shapes the behavior of particles and atoms, but its large-scale effects seem mysteriously muted. It's like hearing 1,000 thunderclaps and finding only a soft drizzle. Something is balancing the books in ways we don't yet understand. Something about the universe allows infinite energy to be borrowed in theory, while only a whisper of it reaches us in practice. The silence is deafening. On a human level, the idea that the universe permits brief, unobservable deviations, fluctuations, borrowings, tremors, touches something deep in our psychology. We are creatures of rules and exceptions. We hope, sometimes desperately, that temporary violations are allowed, that shortcuts can be taken, that debts can be made and repaid without lasting scars. And the quantum world seems to echo that hope, not by violating laws, but by revealing that those laws are far more nuanced than we dared believe. It tells us that perfection is not always precise, that order allows for momentary chaos, and that truth at the smallest scales is smeared across possibility. It tells us that a particle can act out of budget, briefly, and still not be punished, as long as it cleans up after itself. In the end, the quantum world doesn't just allow particles to borrow energy. It is defined by that borrowing. Every electron, every photon, every atom in your body is part of a vast tapestry of interactions stitched together by invisible debts. You are built from particles that were, at one point, almost not there. Your heartbeat, your thoughts, your memories ride on the backs of momentary fluctuations, little flashes of possibility that cancelled themselves out, leaving just enough behind for you to be real. The universe, then, is not an engine of absolutes, but a dance of temporary allowances, a grand theatre of borrowed light. The many worlds may split every time you choose something. Imagine walking down a hallway lined with thousands of doors, some polished and inviting, others cracked and shadowed, each bearing your name. Yet each time you reach for a handle, the hallway behind you vanishes, and another one forms ahead, freshly populated with new doors that never existed until that moment. Every step forward rewrites the architecture of your reality. Every choice, no matter how small, whether to speak or remain silent, whether to turn left or right at a street corner, whether to pick tea or coffee, fractures the universe into a constellation of outcomes, each playing out in a world where you did the other thing. This is not poetry, it is the chilling implication of the many worlds interpretation of quantum mechanics. A theory that suggests that every time a quantum event with multiple outcomes occurs, all outcomes are realized, each in its own branch of the universe. But the part that twists the mind isn't that these worlds exist. It's that they multiply endlessly, blooming from the soil of your choices, splitting and diverging not in silence, but in perfect mathematical choreography. You live not one life, but infinite lives, each drifting farther from the other with every blink of your consciousness. At the quantum level, particles exist in superposition, simultaneously occupying all possible states until they are observed. The classic example is Schrödinger's cat, that infamous feline both alive and dead until the box is opened. In the Copenhagen interpretation, observing collapses the wave function into a single outcome, alive or dead. But Hugh Everett's many worlds interpretation refuses this collapse. Instead, it posits that both outcomes occur and the universe splits, with a version of you observing a living cat and another witnessing death. There is no randomness, no collapse, only separation, only branching. If this sounds fantastical, consider that it solves one of the deepest puzzles in quantum theory, the role of the observer. Rather than assigning magical powers to consciousness, it removes the need for observers entirely. Everything that can happen does happen somewhere. You are not the decider, you are the divider. What makes this theory haunting is not just its logic, but its intimacy. It brings the cosmic scale into your daily life. Every time you choose whether or not to return a stranger's smile, whether to hit send on a message you're unsure about, whether to quit your job or cling to comfort, the universe allegedly cleaves into new realities where each version of you lives out the ripple effects of each decision. Some of these forks are trivial. Some define who you are. Somewhere, there is a version of you who said yes instead of no. Somewhere, you never left that city. Somewhere, you never met the person who changed your life. Somewhere, you never recovered. Somewhere, you did. These are not hypotheticals. They are, in this model, as real as the words you're reading now, except they are unreachable, unseeable, untouchable. Which version are you? The lucky one, the lost one, the one who always wonders? From a scientific perspective, the many worlds hypothesis stems from an elegant refusal to inject collapse into the equations of quantum mechanics. The Schrödinger equation, which governs quantum evolution, is linear and deterministic. Collapse introduces non-linearity, an arbitrary exception. Everett simply said, remove the exception. Let the equations play out. Let all outcomes exist. In doing so, he removed the mystery, but he introduced infinity. Every interaction, every entangled measurement, every tick of time leads to further bifurcation of the universe. This branching happens not only when you make choices, but whenever particles interact in quantum uncertainty. So the proliferation is constant, exponential, unimaginable. The universe is not expanding, it is multiplying. Layering reality atop, reality like mirrors facing each other, spawning infinite regressions of possibility. Still, no one can prove it. This is the uncomfortable truth. The many worlds theory is, in some ways, unfalsifiable, at least for now. We cannot observe other branches. We cannot communicate with other versions of ourselves. The math works, but the evidence hides behind the veil of decoherence. Once branches split, they do not interfere. They evolve independently, causally disconnected. Yet indirect support comes from quantum computing. Quantum bits, qubits, exist in superposition. Their power comes not from being 0 or 1, but from being both until measured. Some theorists argue that quantum computers tap into computations across branches, that they borrow parallel universes to solve problems. This is not proven, but it's not impossible. And if true, then the machine on your desk could be whispering into countless other worlds every time it runs. Philosophically, the implications are seismic. What does identity mean if every version of you exists? What does morality mean if every choice is both made and unmade in some branch? Does guilt survive if somewhere you did the right thing? Does pride endure if somewhere else you failed? The many worlds model doesn't nullify agency, but it reframes it. You are still responsible for your actions in this world, but the knowledge that there are other yous, other paths, can be both a comfort and a curse. Some find solace in the idea that the life unlived is still lived elsewhere. Others are haunted by the thought that every mistake echoes eternally. In some worlds, you love them back. In others, you never met. And in yet others, you never made it past childhood. The branches don't care, they just grow. This framework also redefines fate. If every outcome exists, then destiny is not a line, but a fractal, self-similar, infinite, branching in every direction. There is no single road. There is only a forest of paths, and you are walking all of them. The concept of regret loses its bite, because no choice is final, but it also loses its healing, because no choice is unique. You are not the sole architect of your fate. You are one of many hands shaping many architectures. Each version of you believes itself to be the real one. Each narrates its life as if it is the story, but you are not the story. You are a page in an infinite book, still being written by a quantum pen that never lifts. And yet, there is power in the awareness of this. Power in choosing as if it matters. Because even if all branches exist, you only experience one. Your consciousness rides a single thread, even if it diverges at every node. The others may exist, but you cannot feel them. You are the traveler of this branch, this version, this fragile thread of choices. And perhaps that is enough. Perhaps reality is not about what is out there in the multiverse, but what you carry within you here. Your choices are still sacred, not because they are unique, but because they define your path. You will never meet the you who didn't send the letter, but you will live with the memory of the one who did. And in this way, the many worlds theory, for all its terrifying grandeur, becomes oddly tender. It tells you that your life is not a fluke, but a flowering, that you do not exist alone, but in a family of selves, that your mistakes do not erase your worth, they simply branch the tree. It tells you that reality is wider, deeper, stranger than anything we can see, and that, in choosing to open one door, you honor all the others, even as they vanish behind the walls of worlds you'll never walk. Entanglement can be swapped without direct contact. Imagine if two people who had never met, never spoken, never even existed in the same place at the same time, could somehow share a secret. A whisper passed not through lips or letters, but through the very fabric of the universe. Picture two violinists playing the same haunting melody in perfect synchrony from opposite ends of the earth. Not because they can hear each other, but because a third violinist once stood between them and passed along a tune so precisely entangled in its structure that even after the middle player vanished, the music remained connected. This is the essence of quantum entanglement swapping, a phenomenon so alien to classical thinking that it seems like sorcery disguised as science. It tells us that two particles can become entangled, perfectly correlated in their quantum states, without ever touching, without ever knowing each other, simply because they were once indirectly connected through a common intermediary. In this surreal play of cause and effect, the universe reveals a strange truth. Contact is not necessary for correlation. The bonds that bind the smallest elements of reality are not physical strings or spatial nearness, but mathematical relationships woven invisibly through space-time. To understand the wonder of entanglement swapping, we must begin with the phenomenon of entanglement itself, one of quantum mechanics' most mysterious and counterintuitive predictions. When two particles become entangled, their properties become linked. Measure the spin of one, and the spin of the other is instantly determined, no matter how far apart they are. Einstein famously derided this as spooky action at a distance, because in a classical world, information must travel. No action can happen instantaneously across space, yet entangled particles don't follow this rule. They behave like twins separated at birth who continue to wear the same colors, hum the same songs, feel the same joys and sorrows, even as they live in different cities, and never speak. The strange twist is that these outcomes aren't fixed until one is measured. Reality itself doesn't commit to a version until you look, and when you do, the entangled partner somehow knows. But entanglement swapping takes this even further. It asks, can you make two strangers into twins by removing the twin they never met? Here's how it works. Imagine you have two entangled pairs of particles. Call them AB and CD. Initially, A is entangled with B and C with D. Now you take B and C, two particles that were never entangled with each other, and perform a special kind of measurement on them called a Bell state measurement. This measurement doesn't just observe B and C, it entangles them together. But in doing so, something bizarre happens. A and D, which were previously unconnected, become entangled. The entanglement has been swapped, transferred across space, without direct interaction. A and D now share quantum information as if they had always been partners, despite having no common history. It's as if you took two sets of invisible strings, tied the middle ends together, cut the knots, and suddenly, the remaining strings fused into a new pair. The result is a bridge of information, not built from proximity or communication, but from correlation itself, a kind of cosmic matchmaking. This idea defies everything our intuition tells us about how connection works. In our everyday experience, relationships require interaction. A friend is someone you've met. A signal travels through cables or airwaves. A cause precedes its effect. But in the quantum realm, the architecture of reality is different. Information isn't stored in places. It's stored in correlations. What matters is not where something is, but how it relates to something else. Entanglement swapping exposes this truth in full light. Particles can be linked not by direct paths, but by shared context, by patterns that transcend location. It's a reminder that in the quantum universe, relationships can precede identity. The link defines the particle, not the other way around. The experimental verification of entanglement swapping is no longer theory. It's been demonstrated repeatedly using photons. In these experiments, scientists create two pairs of entangled photons, direct them along separate paths, and perform a Bell state measurement on the intermediate pair. The result? The two outer photons, never in contact, never near each other, exhibit correlations that can't be explained by any classical means. The swap is real, and it has profound implications. It tells us that quantum information can be distributed across a network without the need for direct transmission. It lays the groundwork for quantum repeaters, devices that could extend the range of quantum communication far beyond what's possible with current fiber optics. It opens the door to quantum teleportation across vast distances, using the entangled states as invisible conduits. In this way, entanglement swapping is not just a curiosity. It's the skeleton key to the future of secure, instantaneous, and non-classical communication. But beyond its technological promise lies a deeper philosophical question. What does it mean to be connected? In a world where presence is no longer required for influence, where entanglement trumps interaction, the meaning of together begins to shift. We are taught to believe that distance separates us, that two people on opposite ends of the Earth live in different realities. Yet quantum theory whispers something else. That connection is not a matter of space, but of state, that entangled systems remain parts of a single whole, regardless of geography. In this sense, entanglement swapping becomes a metaphor for the invisible ties between us all. Just as particles can form bonds through a third party, so too do people, connect through shared stories, mutual friends, or common losses. You may never meet the stranger who influences your path, but their presence echoes through your life nonetheless. Consider the implications for identity. If two particles can be bound through entanglement swapping, then identity itself is fluid, defined not by origin, but by linkage. In this view, who you are is not a solitary unit, but a node in a vast dynamic web of relationships. You are not simply yourself. You are also who you affect, who you reflect, who you correlate with. In quantum mechanics, a particle's reality depends on what it is entangled with. Perhaps the same is true for us. Perhaps we exist not as fixed beings, but as evolving intersections, entangled not just with people, but with choices, histories, and possibilities we may never fully comprehend. And this brings us to a final thought. If entanglement can be swapped without contact, then the boundaries we draw between self and other, between cause and effect, between now and then, are not as solid as they seem. Reality may not be a chain of discrete events, but a tapestry of overlapping influences, where unseen links bind seemingly separate elements into a unified dance. Entanglement swapping is proof that even the void between things is not empty. It is charged with potential, with structure, with hidden harmonies waiting to be discovered. It suggests that, at the deepest level of the cosmos, everything is already in conversation, already in relation, already in motion. And maybe that's the strangest and most beautiful truth of all. Quantum fields are the true reality, not particles. Imagine standing in an empty theatre long after the performance has ended. The stage is bare, the props have vanished, and the actors have gone home. Yet there's still something lingering. In the silence, something invisible but undeniably present, like an echo that refuses to fade. Now imagine that everything you thought was real. The actors, the gestures, the stage itself, was never the true show, but merely ripples in the fabric of something deeper, something more fundamental that had been there all along, silent and waiting. This is the unsettling, beautiful truth at the heart of modern quantum physics. That particles, the building blocks we thought composed reality, are not the most basic ingredients of existence. They are illusions, transient excitations of something far more mysterious and omnipresent. Fields, quantum fields, stretching across all of space, never truly absent, always humming with possibility. These fields form the invisible ocean in which all particles are mere waves, flickers, disturbances that rise and fall like temporary songs in a never-ending silence. And in embracing this vision, we do more than revise our science books. We rewrite our understanding of what it means to exist. For centuries, we thought matter was made of tiny, indivisible units, atoms, then electrons, protons, and neutrons, later quarks and leptons. The universe was imagined as a cosmic Lego set built from hard little blocks floating through a void. But quantum field theory shattered that metaphor like a hammer through stained glass. According to this revolutionary framework, particles are not fundamental at all. They are excitations, quanta, of underlying fields that pervade the entirety of space. The electron is not a point-like speck, but a vibration in the electron field. The photon, carrier of light, is a pulse in the electromagnetic field. Every type of particle corresponds to its own field. And the dance of reality is not a ballet of marbles, but a symphony of fields resonating, interfering, entangling. Fields are not confined to particles. Particles are born of fields. The electron you detect in your experiment is just a note played on the instrument of the quantum field. And when the note stops, the field remains untouched and eternal. This revelation flips the intuitive table of reality. We are used to thinking of emptiness as the absence of matter. But quantum fields say otherwise. Even the most perfect vacuum, devoid of all particles, is still filled with fields. These fields never switch off, never retreat. They exist in every corner of the cosmos, even in the darkest gulfs between galaxies. In fact, quantum fields are never truly still. They jitter, vibrate, fluctuate at every moment, producing what we call vacuum fluctuations, momentary surges of energy that pop virtual particles into and out of existence. These fluctuations are not hypothetical. They are measurable, influencing everything from the Casimir effect to the energy levels of atoms. They suggest that space itself is not a canvas on which reality is painted. It is the paint, the brush, the artist, and the frame. Space is fields. Fields are space. And matter, as we perceive it, is simply the shadows cast by the waves of these invisible oceans. But if particles are illusions, brief, localized ripples, then why do we perceive them as solid and discrete? The answer lies in interaction. Our instruments are designed to detect particles because particles are how fields affect us. They are the fingerprints left by field interactions. A detector doesn't see the field itself. It sees where the field rippled hard enough to register as an event, a particle strike. But this is just a byproduct of our limited perspective, like seeing only the tip of an iceberg and assuming it is a floating rock. Beneath every particle is a vast, continuous field. And when you observe a collision in a particle accelerator, you are not watching billiard balls smash. You are witnessing overlapping waves exchanging energy and reshaping each other's patterns. Quantum field theory explains all known forces and matter interactions through this lens. The electromagnetic force is a consequence of the photon field. The strong force is mediated by gluons, ripples in the gluon field, binding quarks into protons and neutrons. The weak force, responsible for radioactive decay, arises from W and S boson fields. And gravity, though not yet fully reconciled with quantum theory, is believed to correspond to a hypothetical graviton field. Even the recently confirmed Higgs boson, the last missing puzzle piece of the Standard Model, is a vibration in the Higgs field, which itself gives mass to particles by interacting with them. Without the Higgs field bathing every corner of the universe, electrons would be massless, atoms wouldn't exist, and there would be no structure, no stars, no you. The fields are not passive. They are the architects of form and function. The cosmos is not a machine built from particles. It is a living ocean of fields whose ripples give rise to everything we call real. But quantum fields don't just give us a new framework. They challenge our deepest philosophical assumptions. What does it mean to be something if that something is just a ripple in an invisible medium? Where does identity reside if the electron in your fingertip is indistinguishable from the electron in a star 10 billion light years away? Because both are merely flickers of the same universal field. We like to believe in separation, in boundaries, in the individuality of things. But the field model whispers a different story. One of unity, of inseparability, of hidden coherence. When you move your hand, you disturb countless fields. You are not isolated. You are a node of activity in a global vibration. Your thoughts, your body, the screen you're reading this on, all are moments of field excitation. And when you die, your fields do not disappear. They simply fall silent, returning to stillness, waiting for the next wave to rise. This picture is haunting, yet strangely comforting. It suggests that we are not fundamentally objects, but events, not things, but patterns. You are not the sum of your atoms, but the way they resonate in fields. And so is everything else. A tree, a mountain, a beam of sunlight, a quantum computer. They are all songs sung by the same silent choir. Each particle, each flicker of energy, each moment of experience is a ripple passing through the fields that underlie everything. To know reality, then, is to listen for the harmony behind the chaos, to tune into the hum beneath the noise. And this hum, this omnipresent vibration, is not static. Fields can interfere, reinforce, cancel. and evolve. The universe is a canvas of superimposed field interactions, an ongoing act of emergence. Nothing is ever truly separate. No particle is ever alone. Every point in space is connected to every other through the continuity of fields. This view collapses the boundary between here and there, now and then. It tells us that locality is a useful illusion, but not a fundamental truth. And it explains quantum entanglement not as magic, but as a natural consequence of shared field and states. When two particles are entangled, their fields are not independent. They are synchronized waves in a deeper, indivisible medium. So when we ask, what is real? The answer is not matter. It is not energy. It is not even particles. The answer is fields. Fields are the bedrock upon which the illusion of matter is built. They are invisible, eternal, and universal. They cannot be isolated, yet they shape everything. They are the silent symphony beneath the noise of phenomena. And if we wish to understand our place in the cosmos, we must stop thinking of ourselves as fragments and start recognizing ourselves as movements in the grand field of being. You are not a collection of particles. You are a wave, a momentary dance in a field that existed long before you and will continue long after. And once you see the world this way, not as a structure of things, but as a choreography of interactions, you begin to notice the subtle rhythm in all things. In the flicker of a candle, the shimmer of heat on pavement, the ache in your chest. When you hear a certain melody, you begin to feel not like an observer of the universe, but like an instrument playing its song. And perhaps, just perhaps, that's what reality has been all along. Not a collection of stuff, but a boundless, resonant field humming its infinite possibilities into being. The quantum Zeno effect, watching something freezes its state. Imagine a candle flame suspended in time, not flickering, not swaying, not even burning, as if the mere act of watching it had frozen the air, halted the combustion, and silenced the room's breath. It's not the wax that refuses to melt, or the fire that refuses to dance. It's your gaze that binds it, your attention that locks it in place. Now imagine, this is not metaphor, but mechanics, not poetry, but quantum physics, where the act of observation doesn't merely record reality, but reshapes it, inhibits it, even traps it. This is the haunting essence of the quantum Zeno effect, a paradox where watching something closely enough prevents it from changing, where measurement itself becomes a form of control, and where the passage of time is not simply endured, but manipulated by awareness. Named after the ancient philosopher Zeno, who challenged the notion of motion with tortuous paradoxes of halves and infinitesimals, the quantum version makes those philosophical riddles manifest in reality. It tells us that a quantum system, when observed continuously, will resist evolution. A radioactive atom that should decay will remain undecayed under constant observation. A quantum particle expected to shift its state will instead remain suspended in the same configuration, as though frozen by the spotlight of awareness itself. And what begins as a strange quirk of subatomic behavior soon metastasizes into a deeper philosophical terror. What if our need to observe the world is the very thing preventing it from becoming? To understand the quantum Zeno effect is to step into a surreal tension between change and attention, between evolution and fixation. At the quantum level, particles do not move continuously like marbles rolling on a floor. They evolve probabilistically, governed by a wave function that determines the likelihood of finding them in any given state. When left undisturbed, this wave function unfolds gracefully over time, like a symphony building toward a crescendo. But the moment we intervene, when we take a measurement, perform an observation, or introduce any act that collapses the wave function, we reset the process. We collapse the uncertainty into a definite outcome, and by doing so, we anchor the system to a single state. Now imagine doing that repeatedly, rapidly, relentlessly, measuring so frequently that the wave function never gets a chance to evolve. The result? Change is stifled, decay is postponed, motion is frozen. This is not science fiction. It has been demonstrated in real experiments. Atoms trapped in magnetic fields, observed with precise intervals, show clear resistance to their natural evolution, as if time itself had developed stage fright in front of our gaze. But this isn't just about atoms in laboratories. It's about the power of attention in shaping outcomes. In a world that encourages constant surveillance, hyper-awareness, and over-analysis, the quantum Zeno effect becomes a metaphor for modern paralysis. How many of us have felt frozen by too much scrutiny? How many dreams wither under the harsh light of perpetual self-monitoring? How many relationships decay not because of neglect, but because of obsessive inspection? In constantly checking whether we are improving, we prevent the very improvement from occurring. In constantly measuring whether we've healed, we prevent the wound from closing. It is as if the soul, like the particle, needs space to unfold, freedom to fluctuate unobserved, to truly evolve. And yet, in our craving for certainty, we rob ourselves of becoming. This paradox haunts not only individuals, but societies. When institutions monitor behavior too closely, through surveillance cameras, biometric scans, algorithmic tracking, they may inhibit the very growth they seek to encourage. People begin to self-censor, to freeze in the roles expected of them, to perform rather than live. Social progress stagnates under the weight of endless scrutiny, and innovation suffocates in environments where every experiment must be prematurely judged. Like the quantum system, a culture too closely watched resists transformation. It performs safety, it avoids risk, it mimics stability, but beneath the surface, it rots in the silence of untested potential. There's a deeper spiritual implication too. If the universe responds to observation, if watching affects being, then perhaps awareness is not a passive act. Perhaps consciousness, at its most fundamental level, is an instrument of reality-shaping power. But this gift is double-edged. While our perception can give meaning, focus can also constrict. The more we fixate on a specific outcome, the more we interfere with the natural emergence of possibilities. A watched pot may never boil, not because the heat is absent, but because time has been fractured by our gaze. In the quantum world, measurement disrupts the dance. In the human world, obsession stifles the soul. And yet, paradoxically, this effect also hints at the power of presence. If mere observation can alter the fate of a particle, then maybe being present, truly present, is not as passive as we believe. Maybe your presence changes outcomes, shifts trajectories, tilts the scales of fate, but only if balanced wisely. There is a difference between mindful observation and obsessive measurement. One nourishes, the other imprisons. One allows becoming, the other enforces stasis. The quantum Zeno effect is not a commandment, it is a warning. Watch wisely, or you may freeze the very life you long to understand. Scientists have pushed this effect into experimental clarity. In 2001, a team managed to delay the decay of atoms by bombarding them with frequent laser pulses, effectively asking them over and over whether they had changed, and finding, surprisingly, they had not. The atoms, like anxious performers, interrupted every few seconds, never reached their act. Their transition was paused not by physical barriers, but by informational ones. This demonstrates something profound, that knowledge, merely seeking knowledge, can influence the reality it attempts to describe. The more we try to pin reality down, the more it slips into the shadows of unchangeability. The observer, it turns out, is not just a chronicler of events, but a sculptor of timelines. What does this mean for our understanding of time itself? That it might not be a river, but a rhythm, something that flows only when left undisturbed, something that accelerates when forgotten and freezes when dissected. The quantum Zeno effect challenges our intuition that time moves independently of us. In this framework, time is relational. Time is not just what clocks measure, it is what the universe becomes in the absence of inspection. The moment you ask the universe what it is doing, it pauses to answer, and in doing so, it delays its own progress. Time bends, stalls, folds in on itself, not because of gravity, but because of attention. The implications ripple outward, touching psychology, creativity, healing, and even love. When you constantly check if you're happy, you're likely not. When you examine love too closely, it becomes brittle. When you overthink every decision, you paralyze the future. The quantum Zeno effect reveals the strange truth that becoming requires a kind of letting go, a surrender to unobserved evolution. In silence, we grow. In darkness, we heal. In mystery, we change. Perhaps this is why the deepest transformations of the soul happen not in moments of clarity, but in murky hours of uncertainty when no one is watching, not even ourselves. So what is the cure for this quantum paralysis? Trust. Trust in process. Trust in uncertainty. Trust in the rhythm of time unmeasured. Learn to look without needing immediate answers. Learn to feel without labeling. Learn to allow states of becoming without force. This is not passivity, it is wisdom. The wisdom to know when your gaze nourishes and when it disrupts. The wisdom to step back so that the seed may sprout, the wave may rise, the soul may shift. Because not everything should be watched. Not every process needs a witness. And sometimes, the greatest power you hold is the power to not look. Particles can tunnel backward in time, mathematically. What if the past isn't behind you but beside you? What if every step forward through time is less a march and more a drift through a fog of possibilities, where the future and the past are not endpoints on a line, but folds in a fabric, curving and curling around each other in ways that defy the rules your senses once trusted? Imagine a tunnel, not one dug through earth, but through chronology itself. A tunnel not made of soil, but of probability. Through it, particles don't merely escape spatial boundaries, they slip across temporal ones. They vanish from now and reappear not just elsewhere, but before. This is not the premise of a science fiction novel. It is the mathematical implication of a quantum reality that bends the arrow of time. Not in poetic flourish, but in calculated equations. And in those equations, particles can tunnel backward in time. At the heart of this mystery lies quantum tunneling, a well-established phenomenon in which particles pass through barriers they seemingly should not be able to cross. It's as if a marble sitting in a valley were to spontaneously appear on the other side of a hill without ever having climbed it. In classical physics, this is impossible, but quantum mechanics dances to different rhythms. In the quantum world, the wave function of a particle, the mathematical description of all the places it could be, doesn't vanish at the edge of a barrier. It leaks, it seeps through, and sometimes, improbably but inevitably, it appears on the other side. This isn't magic, it's math. And when this math is extended into the relativistic domain, where particles are allowed to travel near the speed of light and space-time itself becomes dynamic, a strange implication emerges. The possibility for particles not just to move through space in improbable ways, but to reverse their position in time. In the 1940s, physicist Richard Feynman was working through the behavior of particles in quantum electrodynamics when he stumbled upon a radical reinterpretation that positrons, anti-electrons, could be understood as electrons moving backward in time. This wasn't a speculative metaphor. It was a mathematically valid way to explain the symmetry observed in particle interactions. In the elegant formalism of Feynman diagrams, time is not sacred. Arrows can point backward, and when they do, they still yield accurate predictions of reality. According to this view, an electron moving forward in time and a positron moving backward in time are two sides of the same coin, perhaps the same particle, viewed from different temporal perspectives. Suddenly, time no longer flows like a river. It curls, loops, and folds. But what does it mean for a particle to tunnel backward in time? Isn't time one-directional? Isn't the past fixed and the future open? Not necessarily. In the quantum realm, the rules are probabilistic. Events aren't locked until observed. And in certain rare, highly energetic conditions, Quantum fluctuations allow particles to briefly violate conservation laws, including temporal ones, as long as they correct themselves almost immediately. These events are described as virtual particles that pop in and out of existence, borrowing energy from the vacuum and paying it back almost instantly. But when these particles are viewed through certain mathematical lenses, particularly within the context of Feynman's Stueckelberg interpretation, they can be seen as moving backward in time during that brief interval. Not only does the math allow it, it requires it for the equations to be symmetrical and predictive. And if this behavior exists in the smallest building blocks of matter, then perhaps causality itself is less rigid than we assume. Perhaps what we perceive as cause and effect is merely the statistical average of a vast, chaotic underworld of quantum negotiations, some of which flow forward in time and others backward. In this interpretation, time is not a master, but a servant. It emerges from deeper rules that do not privilege direction. The arrow of time, the belief that time moves inexorably from past to future, is not written into the quantum laws. It is an emergent phenomenon, born from entropy, from the statistical likelihood that systems evolve from order to disorder. But at the quantum level, where entropy doesn't apply in the same way, time may be as reversible as motion, and tunneling backward in time is not forbidden. It is built into the very scaffolding of quantum theory. Now pause. Let that idea settle. A particle could appear in a detector before it ever left the emitter. A signal could arrive before it was sent. A cause could be preceded by its effect, not because the universe is broken, but because we've misunderstood what time actually is. This leads us into one of the deepest chasms of philosophical and scientific tension. If the future can influence the past, even at a microscopic scale, then is the past ever truly closed? Is the present a fixed moment, or a blur of temporal interference, waiting to collapse into form? Are we living in a narrative written from beginning to end, or in a feedback loop where every decision echoes both forward and backward, altering what has been as well as what will be? Consider this. In some versions of the delayed choice quantum eraser experiment, a decision made in the present appears to affect how a particle behaved in the past. When a photon is entangled with another, and one is measured in a certain way, it can retroactively determine whether the other photon behaved like a wave or a particle, even though that behavior should have been decided before the measurement occurred. These experiments suggest that measurement doesn't merely reveal information, it constructs it, and sometimes in ways that stretch our notion of chronology until it snaps. The act of observing now can ripple backward into the then. The future doesn't just follow the past, it defines it. If we accept that possibility, then time becomes not a line, but a dialogue, a conversation between states of being that are not anchored to sequence. And particles become messengers, shuttling not just through space, but between now and then. This is not the sci-fi dream of time travel in a phone booth. It is a mathematically supported dance of probabilities, where time's arrow occasionally twitches the other way, where entropy is king, but quantum laws are anarchists, where the universe we see is just one slice of a larger whole, in which past and future are entangled in a state of mutual influence. And what does this mean for us? If time is not fixed, if the past is not immune to influence, then perhaps we must rethink memory, identity, and causality itself. Are you merely the sum of what has happened, or are you also the result of what has not yet occurred? Does who you are now stretch backward into who you were, reshaping that narrative like a sculptor reworking wet clay? Perhaps intuition, déjà vu, or sudden flashes of insight are not random quirks, but echoes from futures not yet lived. Perhaps consciousness itself is a bridge between what was and what will be, a tunnel through which the self loops, reflects, refracts. In the end, the idea that particles can tunnel backward in time is more than an academic curiosity. It is a tear in the fabric of certainty, a reminder that the universe does not operate on human logic, and that our insistence on linearity may be a limitation of perception, not of physics. The math does not lie, but it does astonish, and it hints at a cosmos far stranger, far less stable, and far more alive than we ever dared imagine. So if particles can loop into the past, even for an instant, then what else can? Ideas, emotions, choices. Is the door we closed yesterday still echoing open? Is the word we almost spoke still rippling across a timeline we cannot see? In the end, quantum theory invites us to step beyond the illusion of now and ask, what if time isn't what we move through, but what we make? Moment by moment, backward and forward in an eternal collapse of possibility. The universe may be a wave function in superposition. Picture standing before a vast mirror, but instead of your reflection staring back, you see every version of yourself that could have existed. The one who took that risk, the one who walked away, the one who stayed silent, the one who spoke up. All of them looking at you at once, none more real than the other, all suspended in a delicate tension of possibility. Now imagine that mirror wasn't just showing you, but the entire cosmos, not as it is, but as it could be, layered in shimmering waves of potential. This is the unsettling proposition at the heart of one of the strangest, most profound interpretations of quantum mechanics. That the universe itself, everything from galaxies to atoms, from your choices to the birth of stars, exists not as a fixed reality, but as a wave function in superposition, a shimmering field of probabilities that has not yet collapsed into a single outcome. In this view, what we call reality is not a snapshot, but a spectrum, a universe suspended between all it could be and what it appears to be, waiting to be observed, waiting to choose. To understand what it means for the universe to be a wave function in superposition, we first need to revisit the quantum bedrock on which this idea stands. In quantum mechanics, particles like electrons or photons don't have definite positions or velocities until they are measured. Instead, they are described by a mathematical entity called a wave function, a cloud of probabilities that represents all the places the particle could be, all the energies it might possess, all the paths it might take. This wave function evolves smoothly according to the Schrödinger equation, a kind of algorithm that predicts how the wave of possibilities changes over time. But crucially, this evolution is deterministic. The weirdness emerges not in the evolution, but in the act of observation. When we measure the system, when we look, the wave function collapses. The cloud condenses into a point. One outcome is realized. All the others vanish. The universe, it seems, waits to be seen before deciding what it is. But here's where things become extraordinary. If particles, the building blocks of matter, exist in this fuzzy, indeterminate state until measured, then why not everything built from them? Why not molecules, cells, brains, planets, stars? Why not the universe itself? This line of reasoning leads to an interpretation known as the universal wave function, championed by physicist Hugh Everett in the 1950s, who proposed that instead of collapsing into one outcome, the wave function never collapses at all. Instead, every possible outcome of a quantum event actually happens. Not in this world, but in branching versions of reality, each as real as the one you experience. In this model, the universe doesn't make choices, it makes copies. You don't just flip a coin and get heads. There's a universe where it's tails, and one where the coin never lands. Every quantum event spawns new realities. Every moment forks. Every possibility lives. This is the foundation of the many worlds interpretation, a deeply unsettling, deeply elegant view of quantum mechanics, in which the entire universe is a constantly branching tree of superposed states, growing infinitely in all directions. It suggests that you, the you reading this sentence, are just one of countless versions of yourself, each inhabiting a different strand of the wave functions unfolding. And while this may sound like metaphysical fantasy, it arises directly from the mathematics of quantum theory. The same mathematics that powers lasers, transistors, MRI machines, and modern computing. In fact, the equations don't demand collapse at all. It's only our insistence on a single, classical outcome that imposes that assumption. Without that insistence, the math flows naturally into a multiverse of quantum branches, each one an echo of a different measurement, a different choice. But if this is true, if the universe is a wave function in superposition, then what does that mean for our understanding of reality? It means that certainty is a story we tell ourselves, that what we call the present is not a defined state, but a slice of an infinite field of possibilities. It means that the past isn't fixed, and the future isn't open. They're both woven into a higher order structure where all timelines coexist, not linearly, but as harmonics in a cosmic symphony. It means that your decisions don't just affect what happens next, they ripple into an ever-expanding web of realities where every next plays out in parallel. You are not the author of a single narrative, but the point of divergence for countless ones, all existing, all valid. This interpretation also reshapes our understanding of consciousness. If measurement causes collapse, and collapse defines reality, then what is doing the measuring? Are we the observers, or are we being observed? And if the wave function includes the universe, then it includes us, the observers, as part of the superposition. Consciousness itself may be entangled with the cosmos, not outside of it, but inside it, as a quantum participant. Some physicists, like John Wheeler, have suggested that the universe requires observers to complete its existence, not as passive witnesses, but as active co-creators of reality. This view, known as participatory anthropic principle, implies a staggering conclusion. The cosmos is not a machine unfolding indifferently, but a mirror, and we are both the ones looking into it and the ones being reflected back. But even as these ideas expand our minds, they resist easy answers. The wave function itself is not something we can see or touch. It is an abstraction, a probability cloud, a mathematical ghost, and yet its effects are real. Experiments in quantum optics, interference, and entanglement confirm time and again that the world obeys the strange rules of superposition. We can place atoms in two places at once. We can entangle particles across vast distances. We can delay measurements and still influence outcomes. Every time we look, we find not certainty, but paradox. And at the center of that paradox is the wave function, silent, invisible, waiting to be collapsed, or perhaps never collapsing at all. So what are we to make of this? If the universe is a wave function in superposition, then we must stop thinking of reality as a snapshot and start seeing it as a process, an unfolding, shimmering, vibrating interplay of all that could be. Our world is not singular, but probabilistic, not fixed, but fluid. And this demands a new kind of humility. It means we can never fully know the world, only the slice we collapse through observation. It means we are forever suspended between what is and what could be, between actuality and potentiality. It means that existence is not a fact, but a flux. And yet, in this uncertainty, there is wonder. Because if the universe is a wave function, then it is not a cold machine, but a living possibility. A poem written in probabilities, a dream dreaming itself, and we, tiny conscious specks within it, are not separate from that wave. We are part of the superposition, entangled with the stars, with each other, with every alternate version of our lives that was never lived, but always possible. In that light, every moment becomes sacred, every choice becomes cosmic, every observation becomes an act of creation. So the next time you question your place in the universe, consider this. You are not navigating a single timeline. You are surfing a wave of being. And in that wave, the universe is not merely something you inhabit. It is something you collapse into focus with every thought, every gaze, every breath. Reality is not what you witness. It is what you co-create. Particles may not exist. Only interactions do. They told you reality was made of things. Tiny, indivisible particles, like miniature marbles bouncing around in the void, forming everything from your skin to the stars, simple and absolute. A cosmos constructed from discrete building blocks. But what if all of that, particles, objects, things, was just a comforting illusion? and beneath the surface there were no things at all, only shadows of connection, echoes of interaction, fleeting whispers of relationships flickering in and out of existence like fireflies in the dark. Imagine standing in a room full of people who never speak, never touch, never acknowledge each other. Now imagine that these people only come into focus when they lock eyes, or when their hands meet, or when a single word passes between them. Until that point, they are fog, potential, not presence. This is the unsettling, beautiful, and deeply transformative core of one of the most radical ideas in modern physics, that particles may not exist in any fundamental sense. Only their interactions, only the act of touching, exchanging, colliding, relating are real. In quantum field theory, what we call a particle is not a little ball or a fixed dot in space, but a ripple, a vibration, a localized excitation in a field that stretches through the entire universe. An electron is not a thing you can point to. It is a wave in the electron field that emerges only when there is interaction, only when energy is exchanged. Without interaction, it is nothing. Without measurement, it is nowhere. The universe, then, is not made of things, but of events, of relationships, of verb rather than noun. And so, to exist is not to be something. It is to do something, to relate, to impact, to change. The moment an electron hits a detector, it becomes real, not because it traveled like a billiard ball from point A to point B, but because the interaction itself was the only thing that existed. Before that, just potential, possibility, a silence waiting for sound. The idea seems almost spiritual, and yet it's mathematically precise. The standard model of particle physics doesn't describe particles as independent entities. It describes how fields interact. What we see, what we call matter, is merely the surface imprint of deeper relationships. An up quark isn't a speck of matter, it's an excitation in the up quark field. A photon isn't a beam, it's an interaction with the electromagnetic field. And when you remove those interactions, strip the math of exchanges, of emissions and absorptions, nothing remains. There is no isolated thing underneath it all. The implications are staggering. It means there is no such thing as intrinsic identity, only role, only action. You are not simply a body, but a vast web of biological, chemical, neurological interactions. The self is not an object. It is a process, a symphony of systems continually dancing in relation to stimuli, memories, feelings, environments. Identity is not what you are, but what you do, and what others perceive in those moments of exchange. In quantum terms, your consciousness, your sense of I, is not a particle floating around your brain. It is the interaction between neural pathways, between perception and memory, sensation and reflection. It is an emergent phenomenon, a chorus that only exists because the voices sing together. This means the universe is more like a conversation than a sculpture, more like a wave crashing against the shore than a stone sitting in stillness. Reality is always becoming, always unfolding, and it is in the moments of contact that truth is born. When a photon meets an atom, when a force field pushes on another, when energy is exchanged, that is when the universe speaks. Everything else is silence, and yet our minds crave substance. We want particles to be things, to have weight and shape and permanence. But at the quantum level, nothing holds still, nothing is solid. The closer you look, the less you find. Try to pin down an electron, and it vanishes into probability. Try to locate a quark, and it recedes behind a curtain of uncertainty. You cannot observe a particle in isolation because isolation is a fiction. Every observation is a dialogue, every measurement a collaboration between observer and observed. The particle doesn't reveal itself. It becomes through the act of observation. This is not mere philosophical musing. It's a cornerstone of modern physics. Quantum electrodynamics, QED, the most precise theory ever built, predicts particle interactions to astonishing degrees of accuracy, not by describing particles themselves, but by calculating how fields interact. Feynman diagrams, those strange, little arrows and squiggles, don't track particles, they track interactions. An electron emits a photon. A quark exchanges a gluon. A neutrino bumps into a neutron. It is the interplay that matters, not the players. And from this, a new picture of reality emerges. One in which objects are illusions, frozen snapshots of dynamic processes. One in which the solid becomes fluid and the real becomes relational. Even space and time themselves, once thought to be passive stages upon which particles move, may be emergent from interaction. The structure of space-time could arise from entangled quantum states, suggesting that not even where and when are fundamental. What is fundamental then? Perhaps nothing. Or perhaps the question is wrong. Maybe the universe isn't built out of bricks, but out of bridges. Connections that flicker into being just long enough for something to happen, and then vanish like footsteps in the sand. And maybe that's what we are too. Not isolated individuals, but events in a vast unfolding, patterns of influence echoing through the fabric of the cosmos. In that view, love is an interaction. Thought is an interaction. Life itself, breath, motion, sensation, is not a property of flesh, but a relationship between systems, cells, chemicals, all reverberating in complex harmony. To exist, then, is not to endure, but to participate, to shape and be shaped, to touch and be touched, even across galaxies, even across time. And when we look up at the night sky, at stars whose light began its journey before humans walked the earth, we are not seeing distant objects. We are experiencing ancient interactions, received by the quantum sensors in our retinas, interpreted by the fields in our brain, and folded into the ever-changing pattern of what we call self. You are not a thing. You are a moment in a cosmic conversation. And the universe does not ask what you are. It asks what you do and how you respond. When it whispers your name through the ripple of a field, quantum information can't be cloned. Imagine you are in a library that contains every thought ever formed, every emotion ever felt, every quantum whisper the universe has ever breathed. An endless hall of consciousness, suspended in the dark. Now picture this. You stumble upon a single book that holds not just a story, but an exact reflection of someone's soul, a perfect quantum memory, unreadable until you open it, but forever changed by your touch. You want to preserve it, to copy it, to hold it in multiple places at once. But the moment you try to make a clone, something strange happens. The original begins to fade, distort, or resist. The universe steps in and says no, not because it's being cryptic, but because at the deepest level of reality, quantum information isn't like a book or a file or a song you can burn onto a CD. It's alive. It's singular. And in the quantum world, uniqueness isn't a limitation. It's a law. This is the no-cloning theorem. A principle that declares, with unsettling certainty, that quantum information cannot be copied. Not just that it's hard or inconvenient, but that it is fundamentally impossible. Unlike classical information, which you can duplicate endlessly without cost, print a page, duplicate a file, replicate a string of bits, quantum information resists cloning at its core. Because when you try to duplicate an unknown quantum state, you aren't just making a copy of data, you're trying to replicate the exact probability amplitudes, the phase relationships, the delicate superpositions that define the soul of a particle. And these states are not something you can just read off without collapsing them. To observe is to interfere. To measure is to change. And so, the very act of attempting to copy a quantum state becomes self-defeating, because it demands knowledge you cannot extract without destroying the thing you wish to preserve. Think of it like trying to copy a snowflake with your bare hands. The moment you touch it, it melts. Try to photograph it, and the flash disrupts its structure. You can describe it, sketch it, even simulate it, but you cannot clone its perfect, intricate identity. The no-cloning theorem emerges not from mysticism, but from the hard math of quantum mechanics. It was formalized in 1982 by Wouters and Zurek, and its proof is elegantly simple. If you could clone any arbitrary quantum state, you would violate the linearity of quantum evolution. The Schrödinger equation, the heartbeat of quantum mechanics, insists on linearity, and cloning would shatter that structure. You cannot preserve coherence and create a duplicate at the same time. And this isn't just a quirky side note, it's a law with profound consequences. It underpins the very security of quantum cryptography. Because quantum keys can't be cloned, eavesdropping on a quantum channel becomes detectable. If someone tries to intercept and replicate the quantum key, they will inevitably disturb it, exposing their presence. Quantum information is protected not by locks, but by physics itself. The no-cloning theorem also reshapes our understanding of teleportation. Not the Star Trek kind, but quantum teleportation, where the state of a particle is transferred from one place to another without physically moving the particle itself. In this process, the original is destroyed, because to send quantum information, you must erase the source. You cannot have it both here and there. Entanglement enables the transfer, but it never allows duplication. You aren't copying the particle, you're translating its identity through a fragile quantum bridge. And that's what makes it beautiful. The theorem also touches the heart of quantum computing. In classical systems, redundancy is your safety net. You make backup copies, you correct errors with duplicates. But in quantum systems, redundancy becomes impossible. You must find entirely new ways to protect and preserve information through error correction codes that cleverly entangle multiple qubits, through topological systems that encode information in braids and twists rather than bits and bytes. The very architecture of a quantum computer must dance around the fact that its building blocks can never be cloned. Philosophically, this speaks to a deeper idea, that identity in the quantum world is not something that can be extracted and frozen. It must be respected, held delicately, and accepted in its ephemeral nature. A quantum state is a secret it only tells once, and if you miss it, it is gone. This uniqueness stands in stark contrast to our modern digital culture, where everything is duplicated, streamed, copied, cached. We live in a world where nothing feels scarce because anything can be reproduced. But in the quantum domain, scarcity is truth. Each state is a singular performance, like a jazz improvisation that cannot be replayed the same way twice. You can remember it, you can be moved by it, but you cannot recreate it. There is also something deeply human in this law. It reminds us that no two people experience a moment in the same way. That memory is not duplication. That love is not transferable. That our identities, our experiences, our emotions are not things that can be cloned. Even when we try to tell someone exactly how we feel, something is always lost in translation. Language stumbles. The quantum coherence of feeling collapses into classical speech. And just like a quantum state, the essence of who we are can never be fully copied, only approximated, only interpreted. This is why authenticity matters, why every connection, every glance, every idea shared between minds is precious, because it exists only in the interaction, in the entanglement, in the now. The no-cloning theorem isn't a restriction, it's a revelation. It tells us that the universe is not a place of infinite copies, but of singular encounters. It says that to know something truly, you must meet it as it is, not through replication, but through relationship. And it challenges us to rethink not just physics, but identity, trust, and the boundaries of what can be known. In a world where everything can be forged, cloned, and synthesized, quantum mechanics reminds us that some things, perhaps the most important things, cannot be duplicated. They can only be lived. Quantum fields are the true reality, not particles. Imagine you're sitting on a quiet shore staring out at the ocean. But this ocean behaves unlike any you've ever known. It ripples before the wind touches it. It responds to a thought, and, sometimes out of nothing but the swirl of a wave, a solid object briefly appears, dances on the surface, and disappears again. Now imagine if someone told you that everything you've ever seen, touched, or believed to be solid, your body, the screen you're reading this on, the earth beneath your feet, is nothing more than such dancing crests of invisible waves. That reality itself is not built from particles at all, but from vast, underlying fields rippling through the universe like that strange ocean. This is not speculative poetry or mystical metaphor. This is the most consistent and powerful explanation modern physics can offer, that at the deepest level of existence, there are no particles, only quantum fields, continuous and dynamic, whose vibrations give rise to the illusion of matter. For centuries, we believed that the universe was composed of tiny, indivisible bits of stuff, atoms, and then subatomic particles like electrons, quarks, and photons. They were thought to be the ultimate Lego blocks of reality, but with the rise of quantum field theory, this image began to unravel. Physicists came to understand that particles are not independent entities flying through space like miniature marbles. Instead, they are excitations, disturbances, if you will, in their respective quantum fields, much like ripples on a pond surface. An electron is not a point-like bead. It's a tiny localized ripple in the electron field. A photon, similarly, is a ripple in the electromagnetic field, and the so-called vacuum of space, which we once thought of as empty, is not empty at all. It's a seething, restless ocean of potential, a quantum field that permeates all of existence, restless even, in its lowest energy state. These fields are not passive. They're the very fabric from which reality emerges. This concept is so counterintuitive that it demands we abandon the way we usually think about things. We're used to assigning identity and substance to objects. A chair is a thing, a stone is a thing, you are a thing. But in quantum field theory, things are merely temporary arrangements of field vibrations, localized in space and time. The field is fundamental, the particle is a momentary flare. Think of a guitar string stretched taut. When plucked, it creates a standing wave, a vibration that manifests as a musical note. Now imagine the universe as a collection of invisible strings, fields, each capable of vibrating in unique patterns. When these fields are excited in just the right way, they generate what we perceive as particles, which then combine into atoms, molecules, and the rich tapestry of forms we associate with reality. But strip away the excitement, dampen the ripples, and the particle vanishes. There is no bead left behind. There is no core. There is only the field, silent and omnipresent. This has profound implications for how we understand everything, from the nature of existence to the illusion of individuality. If you are composed of particles, and those particles are merely excitations of fields, then in a very real sense, you are not a distinct object moving through space. You are a region in which multiple fields, electron, quark, Higgs, gluon, are vibrating in concert, harmonizing briefly into the pattern we call you. And when these vibrations fade, when the body ceases, it is not as though something solid disappears. Rather, it is the music ending, the waves falling still. The field remains, always, eternal. Every force, every object, every interaction is a story of field meeting field. When an electron repels another, it's not two particles shoving each other like magnets. It's their fields overlapping, exchanging virtual photons, field ripples, in an invisible handshake. When light travels from a star to your eye, what moves through the void is not a stream of particles, but a coherent fluctuation in the electromagnetic field. Even the phenomenon of mass arises not from some inherent weight in particles, but from their interaction with the Higgs field, a scalar field that fills the universe like a molasses fog, slowing some field vibrations more than others, giving rise to the inertial resistance we interpret as mass. Without the Higgs field, particles would be massless. They would fly at the speed of light, unable to clump into stars, planets, or life. This is the power of fields. They don't just host particles, they define their properties. But perhaps the most astonishing aspect is that these fields are not local. They stretch across the entire cosmos. The electron field that gives rise to your body is the same field present in a distant galaxy. When a particle is created, it is the field itself responding at a specific location. It's not that a new object is born. Rather, the field momentarily reveals a vibration at that point. And when particles entangle, it's not magic. It's the underlying field entering a non-separable state, one that defies locality and linear causality. Quantum fields are not just the stage. They are the actors and the play and the theater itself. They underlie not only matter and force, but also space and time. Some physicists speculate that space-time itself may be emergent, a macroscopic appearance, generated by deeper quantum fields. If this is true, then the universe does not sit inside space. Space arises within the structure of quantum fields. Time, too, may not be fundamental, but a reflection of how these fields evolve in relation to each other. We are only beginning to scratch the surface of what this means. In the mathematics of quantum field theory, everything is described in terms of operators acting on a vacuum state, shifting the field into different excitation levels. It is through this dance of energy and probability that particles flicker in and out of being. Yet the field itself, the ever-present sea, is unshaken, a continuous presence underneath the ephemeral. And so the question arises, if everything we observe is just the shimmering surface, what is the true nature of the field itself? Is it conscious? Is it woven with information? Some interpretations suggest that information is the most fundamental currency of the universe, not mass or energy, but bits, encoded in the ways fields relate and transform. This brings us uncomfortably close to philosophical territory. If particles are illusions and fields are the real actors, then identity, separateness, and permanence become questionable ideas. You are not a fixed object. You are a standing wave in a cosmic song, and so is everything else. In this view, death is not destruction, but disintegration of a localized coherence. The field remains. The possibility of recombination, of new excitation, is ever present. Life becomes a temporary symphony of overlapping fields. Reality becomes less a collection of things and more a choreography of happenings. And all of it, stars, thoughts, love, decay, is ripples on an invisible sea. When you look up at the night sky and see starlight that traveled millions of years, you're witnessing a field that never slept. When you touch another person, it's not their particles you feel. It's the push and pull of their quantum fields, brushing against your own. The illusion of separation melts in this understanding. Everything is connected, not metaphorically, but physically, through shared fields that span the universe. To know this is to feel small and vast at once. You are not a rock in a river. You are the ripple in the current. You are not in the universe. You are the universe, vibrating here and now as a temporary, beautiful distortion in the quantum field. You might never know if the wave function collapses or not. Imagine stepping onto a vast, darkened stage where no script has been written, no actor has taken position, and no spotlight has chosen a subject. Yet the theatre hums with the soft, trembling energy of possibilities. The air vibrates faintly, as if anticipating a performance that hasn't yet begun, and somewhere beyond the silence, a symphony waits to be called into existence. But here's the paradox. The orchestra might already be playing, softly, invisibly, or it might not exist at all until an audience sits, a light turns on, and someone decides to look. In this strange theatre of the universe, the wave function. The mathematical hymn that describes all that could happen may or may not collapse. And the more deeply you look, the more elusive the answer becomes. You might never know if the symphony plays when no one listens. You might never know if the wave function truly collapses, or if collapse is merely an illusion projected by your need for conclusions. For at the heart of quantum mechanics, nestled between possibility and observation, is a question so profound, so unresolved, that it shakes the foundations of what we think it means for something to exist. Unlike classical physics, which paints a picture of definite states and predictable outcomes, quantum mechanics proposes a realm where reality is not a static photograph, but a swirling haze of probabilities, each coexisting in a fluid superposition, like chords held in suspension until one is struck. This is not just poetic imagery, it is the backbone of the most successful scientific theory we've ever devised. In this theory, the wave function is a complete description of a system, not telling you what is, but what might be. It evolves smoothly and deterministically according to the Schrödinger equation, until it seems a measurement is made. Then suddenly, the symphony stops being all possible songs at once and becomes just one. A note is chosen, the curtain lifts, a particle appears in one place. But why? And how? And does this collapse actually happen? Or is it just an illusion, a sleight of mind born from interaction between observer and observed? The truth is, physicists still don't know. This isn't ignorance born of laziness or oversight. It is a fundamental blind spot woven into the very structure of quantum theory. The Copenhagen interpretation, the oldest and once most widely taught, simply accepts collapse as a given. You look, and reality snaps into place. But other interpretations, like the many worlds hypothesis, decoherence theory, objective collapse models, and quantum Bayesianism, paint a far stranger picture. Perhaps all outcomes happen in branching worlds where every possibility is real. Perhaps collapse is not physical, but psychological, a shift in your knowledge, not in the system itself. Perhaps wave functions never collapse at all, and what you call reality is just your narrow slice of a grand, uncollapsed whole. And if that's the case, if the wave function never collapses, then what you see, the electron here instead of there, the photon reflecting instead of transmitting, is not reality crystallizing, but your mind drawing borders in a borderless sea. But here's the twist. You can't know. Not just that you don't know, you might never be able to, because the difference between collapse and no collapse may be empirically indistinguishable. The mathematics gives the same predictions either way. Whether you believe the universe splits into countless worlds every time a choice is made, or whether reality truly snaps into place when a detector clicks, or whether all of it is just an elaborate statistical game, none of these views can currently be confirmed or denied by experiment. You are trapped inside the show, watching the play unfold, with no access to the wings or backstage. The curtains may or may not exist. The actors might not even be real. And this opens a chasm of philosophical consequences. What is real if you can't know whether what you observe is all there is? What does it mean to measure something if the act of measurement changes the very thing being measured? Are you simply collapsing a wave function or creating a fact that did not exist before you looked? Imagine a pond of still water in a forest no one enters. Is it truly still? Or is that question meaningless without the splash of a pebble? You might say, but surely the moon is there even if I don't look, echoing Einstein's famous objection. Yet quantum mechanics whispers a more haunting reply. The moon is a probability wave, a fuzz of possibility, until something or someone interacts with it. And even then, it might not be a collapse, but merely your entanglement with the system, a mutual dance that gives birth to meaning. In the quantum realm, measurement is not passive. It's a handshake, a mutual corruption. The observer becomes part of the system, and the system includes the observer. That blur between subject and object, between question and answer, is not a failure of understanding. It is the understanding. And this is where metaphysics begins to echo physics. Perhaps the universe is not made of things, but of interactions. Perhaps particles are not fundamental, but epiphenomena, bumps on the sea of quantum fields, temporary resonances in the vibrating nothingness of the vacuum. Quantum field theory tells us this: particles are not marble-like nuggets flying through space. They are excitations in invisible fields. A photon is a ripple in the electromagnetic field. An electron, a ripple in the electron field. The Higgs boson, a wave in the Higgs field. Space itself seethes with virtual particles, fluctuations, probabilities. The vacuum is not empty. It is a stage of infinite unrest, a symphony of unsounded notes. The illusion of solidity, the illusion of certainty, the illusion of knowing. These arise only when you choose to look, and by then, it may be too late. The wave has collapsed, or so you think, but maybe it never did. Maybe the act of collapsing was just the story you told yourself afterward to make sense of the world. And yet, despite all this uncertainty, the predictions work. Quantum mechanics is the most successful predictive framework in the history of science. It builds lasers, transistors, GPS systems, MRI scanners. It maps the structure of atoms and predicts the behavior of particles in high-energy accelerators. It works, not despite the mystery, but because of it. Because it accepts that reality is not an answer, but a question, a waveform, a curtain, never fully drawn. And in that sense, you are quantum too. Your thoughts, your choices, yourself. These may not be fixed particles but fluctuating states. The you that makes a decision, the you that observes the world, may be entangled with the very thing you think you're separate from. You are not outside the experiment. You are in it. You are the detector and the wave, the question and the answer, the silence and the song. And so, when you ask whether the wave function collapses, you're asking something deeper. Do I shape reality, or do I merely reveal it? Is the universe waiting for me to choose, or has it already chosen and I am just catching up? Is there a single world, or a branching tree of infinite variations, each one containing a version of me asking the same question, in slightly different words, with slightly different outcomes? And is the truth even knowable if the knowing changes? The truth? You might think that sounds hopeless, but it isn't. It's the most liberating realization of all, because it means that certainty is not required for wonder. That reality does not need to collapse to be beautiful. That ambiguity, that haunting fuzz between what might be and what is the music. The song of the universe is not one note. It is all notes, trembling in superposition, waiting not to be fixed, but to be felt. You might never know if the wave function collapses, but maybe the question isn't whether it does. Maybe the real question is why you needed it to. Spin isn't rotation. It's a quantum property with no analogy. Imagine holding a perfectly still coin between your fingers, suspended in the air so delicately it seems frozen in time. No movement, no blur, no sound. You stare at it, sensing its stillness, and then someone whispers, "It's spinning." Confused, you look again, certain that nothing is turning, no rotation, no revolution, not even a tremble. And yet, in the quantum realm, this is precisely how spin works. Not as a rotation you can see or feel, but as a property that is, even when it looks like nothing is happening at all. Spin isn't a twist, a turn, or a twirl in space. It's a label for something stranger, something fundamental, something that has no true counterpart in our everyday world. The moment we say spin, our minds leap to analogies. A spinning top, a wheel in motion, the earth rotating on its axis. But quantum spin laughs gently at our metaphors. Because in the microscopic universe of particles, spin isn't something we can picture. It's not the kind of motion that leaves a blur or can be caught on camera. It's intrinsic, built into the identity of particles like electrons, quarks, and neutrinos. Not because they're turning in space, but because they carry a quantum fingerprint that defines how they behave, how they interact, and how they align with the invisible symmetries of the cosmos. Imagine trying to explain color to someone who sees in grayscale. How do you describe red without falling into contradiction? Now try explaining spin to someone steeped in classical intuition. It is directionless direction, motionless, momentum, invisible influence. It's what determines magnetic behavior, dictates statistical laws, and underpins the architecture of the standard model. And yet, it defies all analogies drawn from the macroscopic world. It is, perhaps, the clearest signal that the quantum world is not a smaller version of ours, but a realm with its own logic, its own language, and its own meaning. To physicists, spin is quantized angular momentum, meaning it comes in discrete values, not continuous variations. For electrons, that value is 1/2 in units of the reduced Planck constant h, meaning if you try to rotate the particle 360 degrees, it doesn't come back to its original state. You have to turn it twice, 720 degrees, to return to where you began. This bizarre fact has been tested, confirmed, and built into the very heart of quantum theory. It's not a metaphor, it's a mathematical truth, and it implies that particles like electrons aren't tiny spheres spinning on an axis. They're quantum objects described by spinor wave functions, whose very structure changes in a way utterly foreign to classical thinking. Picture a Mobius strip, a surface with only one side and one edge. Trace your finger along it, and you'll come back to your starting point only after 2 loops. That's not just a quirky shape. It's a crude metaphor for how quantum spin behaves. But even this falls short, because the spin of an electron isn't something you can point to or photograph. It isn't even located in space in the way position or velocity might be. Instead, it's part of the algebra of the particle's identity, woven into its equations, dictating how it responds to fields, how it obeys or defies the Pauli exclusion principle, and how it participates in the cosmic dance of matter. And yet, spin has consequences you can observe. The entire periodic table, the structure of atoms, the stability of matter, the existence of chemistry, arises from it. Spin determines whether particles are fermions or bosons, whether they obey the exclusion principle, like electrons, in atoms, or pile into the same state, like photons in a laser. The fermions build the world, the bosons mediate its forces. Spin is the divide, the binary switch between matter and force. It's what tells the universe how particles stack, how they interact, and whether they can even share space. This simple quantum number governs everything from magnetism to superconductivity, from the formation of stars to the fusion that powers the sun. And it has nothing to do with spinning in space. It emerges not from motion, but from symmetry. At the heart of modern physics lies a truth more profound than any visual metaphor. Nature is shaped by symmetries. The laws of physics are the same here as they are over there, the same now as they were then. And every symmetry gives rise to a conserved quantity, a kind of cosmic accounting rule. From spatial symmetry comes momentum, from time symmetry, energy, and from rotational symmetry, from the idea that the laws don't change when you spin your frame of reference, comes angular momentum. But quantum spin is deeper than classical angular momentum. It isn't about rotating in a space, it's about how particles transform under symmetry operations. The electron's spin of 1-2 tells us that its wave function lives not in 3-dimensional space, but in a more abstract space of SU2 symmetry, a mathematical structure that defies visualization. These transformations define how particles behave under rotations, but they aren't rotations themselves. They're deeper, they're structural, they define what a particle is. And this is where philosophy enters. If something can behave like it spins, cause magnetic fields, obey rotational rules, affect other particles, and yet not rotate, then what does it mean to call it spinning? What does it mean to be anything at all? You are taught to think in images, a spinning ball, a turning gear, a rotating planet. But the universe is not built from pictures. It's built from principles, from the unseen, the unvisualizable, the algebraic. And spin stands as a monument to this truth, that not all that is real can be drawn. The Higgs field too plays a part. It is through interaction with this field that certain particles gain mass. But spin persists whether the particle is massive or massless. The photon, with spin 1, is massless. The electron, with spin 1 or 2, gains mass through the Higgs. Yet both have spin, a quality unaffected by the inertia the Higgs grants. Spin, then, is deeper than mass, deeper than motion. It is intrinsic, it is eternal. It is the identity card of the particle, stamped at birth and unchanged by time. And even in the seething vacuum, where fields fluctuate and virtual particles blink into and out of existence, spin remains a conserved and crucial quantity. The entire structure of quantum field theory, the most precise theory ever devised, rests on how these spins interact, how fields with different spins mediate forces, how the universe's tapestry is threaded not by particles as such, but by excitations in spinning fields. You live in a world where every magnet in your hand, every electronic device, every beam of light, every burst of energy, all of it is governed by spin. And yet, if asked what spin is, you could only answer in abstractions. You can't point to it, you can't see it, you can only know it, through its effects, its rules, its mathematical skeleton. Like a ghost in the machine, it is there and not there, real but not visible, actionable but not picturable. This is the elegance of quantum reality. It does not care if it can be understood in pictures. It only cares that it is consistent, that it explains, that it predicts. And spin predicts with surgical precision. We have measured the magnetic moment of the electron to 11 decimal places, and it matches theory exactly. This isn't just precision. It is revelation. The universe is telling us spin is real. Not spinning, not rotation, but spin. So if you ever feel disoriented by the idea that reality can't be imagined, can't be drawn, can't be held in your mental hands, take comfort. You're not alone. Every physicist who truly understands spin feels this disorientation, because spin is the place where language collapses, where metaphor dies and only mathematics survives. It's a reminder that the universe is not here to be intuitive, it's here to be itself. And so are you. You too have qualities that cannot be seen, traits that define you regardless of your outer motion. You too carry symmetries and contradictions. Like a particle with spin, you may look still and yet be turning through spaces no one else can see. Your mind might change when no one is watching. Your essence might not live in your actions, but in the pattern of your possibilities. You are not what you seem, and neither is the electron. Reality, it turns out, is not a surface. It is a structure, a lattice of rules, relations, and resonances. And spin, strange, silent, and unseen, is one of its purest songs. You don't need to picture it to believe it. You don't need to understand it to feel its presence. Just know that behind every atom, every beam of light, every breath, there is a spin, not rotating, but singing. And though its voice is beyond metaphor, its truth is everywhere. The measurement problem has no consensus explanation. Imagine standing before a mirror that doesn't reflect your image, but your potential. Not what you are, but all the infinite versions of you that could be. One mirror shows you speaking, another silent. One shows you turning away, another reaching forward. The room is filled with mirrors, each offering a different outcome, a different moment, a different reality. And you, the observer, the participant, are caught in the center of them all, wondering which one is real. But here's the catch. None of them solidify until you decide to look, and even then, you're not quite sure what looking means. In the quantum world, this is the heart of one of the most unsettling and unresolved questions in all of science: the measurement problem. It is not just a puzzle about particles or devices, but a challenge to our very understanding of existence, observation, and reality itself. For in quantum mechanics, the act of measurement does not merely reveal reality, it appears to create it. Before a particle is measured, it exists in a superposition, a delicate symphony of all possible states. It is not here or there, spin up or spin down, but both and neither. A wave of possibility governed by the Schrödinger equation, evolving smoothly and predictably. But then, something happens. A measurement is made, and the wave function collapses. Suddenly, one possibility becomes real, the others vanish, and the particle is found to have a definite property. This collapse is abrupt, irreversible, and, perhaps most strangely, not described by the equation that governs everything else in quantum theory. It's as if a play is being written as it is performed, but no one agrees who the playwright is or whether the script existed before the curtain rose. And though the theory predicts outcomes with uncanny precision, it says nothing about when or how the collapse occurs. That silence at the core of quantum mechanics has been a source of philosophical tension for nearly a century. Unlike classical theories, which offer a clear and complete picture of what the world is. Quantum mechanics offers only a probability of what you might find, and that probability depends on how and whether you look. But what is a measurement? Is it the interaction with a machine, the registration of a detector, the moment a conscious observer sees the result? Or is measurement simply another form of entanglement, a spreading of quantum information that ripples through the environment until classical certainty emerges? Each interpretation offers a different answer, and none has achieved consensus. The Copenhagen interpretation, long dominant in physics, suggests that reality doesn't exist until it is observed. That's not metaphor. It's the literal claim that physical properties are undefined until measured. In this view, observation causes the collapse. But this raises more questions than it answers. What counts as an observer? A human mind? A camera? A cloud chamber? And why should consciousness, which evolved billions of years after particles did, be the thing that gives the universe its form? The many worlds interpretation answers differently. The wave function never collapses. Instead, every possible outcome actually happens, but in separate, non-communicating branches of the universe. When you open Schrödinger's box, you don't collapse the cat's wave function. You split into two versions of yourself. One who sees a living cat, and one who sees it dead. This view avoids the mystery of collapse, but at the cost of infinite realities, constantly branching with every quantum event. Is that a price we're willing to pay for coherence? Other models propose spontaneous collapse, the idea that wave functions randomly, but rarely, collapse on their own, with no need for observers. The GRW model, for instance, suggests that collapse is a physical process governed by probabilistic rules, like radioactive decay. But despite being elegant, on paper, such models require new constants and mechanisms that have never been directly observed. Decoherence offers yet another route, not as an interpretation, but as an explanation for why quantum behavior vanishes at macroscopic scales. It suggests that interaction with the environment causes superpositions to spread out and become effectively classical. But decoherence doesn't solve the measurement problem. It only explains why we appear to see classical outcomes. The central mystery remains: what singles out one result from the many? Even quantum Bayesianism, cubism, reframes the question entirely, asserting that quantum states are not real objects, but expressions of personal belief, updated by experience. In this view, the wave function reflects the observer's knowledge, not an external truth. Collapse is not a physical event, but a mental update, a Bayesian revision in light of new data. Yet for all its philosophical nuance, cubism faces its own challenges. For if quantum states are subjective, how do different observers agree on outcomes? And if reality is observer-dependent, what anchors it across time and space? The question of measurement touches on deeper metaphysical questions than physics alone can answer. What does it mean to observe? What does it mean for something to be real? Is the universe a deterministic machine that hides behind uncertainty, or a probabilistic ocean where certainty only emerges through interaction? And more profoundly, are we part of the system or apart from it? In the classical world, observers are external. We look at a thing, and it stays what it is, regardless of our gaze. But in the quantum world, observation is participation. You cannot look without touching, cannot measure without changing. This is not a flaw in the theory. It is its essence, and it forces us to ask not just what reality is, but what role we play in it. Perhaps the very division between observer and observed is artificial. Perhaps the universe does not split cleanly between subject and object, but flows as a unified whole, a web of entanglements where everything affects everything else. In that view, measurement is not a collapse or a choice or a special moment. It is the natural unfolding of the universe's structure, seen from within. And that would mean that your every thought, your every question, your very act of wondering about the measurement problem is part of the measurement. You are not outside the equation. You are entangled in it. You are a term in the wave function, a node in the cosmic algorithm. And every time you ask what is real, the universe replies with a mirror. What do you mean by real? But the mirror never gives a final answer. It shows possibilities, not conclusions. And this is the agony and the beauty of the measurement problem. It reminds us that knowing is not separate from being. That certainty is not a property of the world, but a moment in your mind. That perhaps the universe does not contain answers, only questions that evolve, observers that change, and truths that flicker into place only when you dare to look. So here we are, almost a century after quantum mechanics first shattered, the glass of classical certainty still staring into the fog, still unsure whether it is lifting or thickening. The equations work, the predictions match, the experiments deliver, but the meaning, the why, remains elusive. And no matter which interpretation you favor, Copenhagen, many worlds, objective collapse, decoherence, cubism, each reveals a different facet of the same unresolved riddle. The measurement problem is not just a bug in our equations. It is a window into the nature of existence. It is a philosophical crossroads disguised as a scientific puzzle. It is a reminder that the world is stranger than our minds are comfortable with, deeper than our metaphors can capture, and more participatory than we once believed. And maybe that's the point. Maybe the goal of physics is not to erase mystery, but to frame it more clearly, to give us better questions, sharper mirrors, and deeper awe. Because in the end, it might not matter whether the wave function collapses or splits or decoheres or updates. What matters is that when we look, we see. And that moment, when a pattern emerges, a particle appears, a number clicks into place, that is when the universe becomes real for us. Whether that reality existed before or only now is a question that may never be resolved. And yet, it is the very question that makes us human. To wonder, to measure, to seek meaning in a world that might only reveal it when asked. Electrons don't orbit the nucleus. They exist in probability clouds. They taught you that atoms were tiny solar systems, a dense sun-like nucleus surrounded by little planets called electrons, each obediently circling in neat elliptical orbits, an elegant dance of matter at miniature scale. And you believed it because it made sense, because it was visual, because it mirrored the grand celestial choreography above us. But that image, comforting and orderly as it was, is a lie, a pedagogical placeholder for something far stranger, far less visible, and infinitely more true. Electrons do not orbit the nucleus. They do not whirl like marbles in motion, nor trace predictable paths in the void. Instead, they exist as smears of possibility, as haunting probability clouds, diffuse, uncertain, statistical whispers that suggest where an electron might be, but never tell you where it is. In the quantum realm, location is not a fact, but a fluid. Electrons are not in places. They become places when observed. And even then, the act of observation collapses a vast field of probabilities into a single ephemeral outcome. Before you looked, the electron was not here or there. It was a haze, a presence without position, a question mark smeared across space. This is the quantum reality. The neat Newtonian model of orbiting electrons has dissolved under the microscope, of deeper physics replaced by Schrödinger's equation, which does not describe a path but a wave function, a mathematical symphony that defines the likelihood of presence, not the presence itself. These clouds are not just metaphors. They are real, empirically verified through countless experiments. When we measure the energy levels of atoms, when we probe the behavior of electrons with lasers and magnetic fields, when we use scanning, tunneling microscopes to visualize the boundaries of these clouds, the data does not reveal paths or orbits. It reveals patterns of probability, nodal structures where electrons are more likely to be found, and forbidden zones where they are not. And these structures, spherical shells, toroidal lobes, strange flower-like shapes, are not imagined. They are dictated by the mathematics of wave functions, constrained by the fundamental symmetries of space, by the Pauli exclusion principle, and by the quantum numbers that govern spin, angular momentum, and energy. Each electron in an atom occupies a quantum state, a cloud-shaped possibility field, and no two electrons in the same atom can share the exact same state. This isn't artistic license, it's why matter has structure. why atoms have volume, why your body doesn't fall through the chair you sit on. The firmness of the world is built not on certainty, but on forbidden sameness. Electrons refusing to occupy identical roles, forced by exclusion to spread out in space, to inhabit different clouds, to give atoms their depth. And these clouds, these regions of high probability, are not static. They shimmer with potential. The electron is not hiding in a fuzzy ball, waiting to be caught. It is the fuzz. It is the potential. It does not exist apart from the probabilities. It is the probability. And this defies all classical logic. You cannot say, the electron is in this place, I just don't know it yet, as you might say for a hidden coin under a cup. That's not how quantum reality works. Until measured, the electron does not have a position. It has a distribution. Your very question, where is it, must be rephrased. The universe at this scale does not speak in absolutes. It speaks in amplitudes, likelihoods, patterns of maybe. And even more unsettling, when you do measure the electron's position, the wave function collapses, the cloud vanishes, and for a brief moment, the electron is somewhere, only to resume its ghostly spread the instant you stop looking. This interplay between presence and possibility, between observation and being, is not an abstract philosophical curiosity. It is the essence of how matter behaves. It explains the periodic table, the strength of chemical bonds, the shapes of molecules, the fluorescence of light, the stability of matter. Your very existence depends on these clouds. The fact that electrons do not spiral into the nucleus, the fact that they resist compression not through force, but through quantum identity. Electrons are not orbiting suns. They are fogs of influence, shaped by fields, constrained by symmetries, sculpted by equations. And those equations, arising from quantum field theory, governed by the Higgs mechanism, constrained by vacuum fluctuations, tell us that particles are not particles in the classical sense. They are excitations in fields, disturbances in an invisible ocean of potential. The electron is a ripple in the electron field. It is not a dot in space, but a waveform. And when that waveform exists within an atom, it is shaped into stationary states, not motionless, but unchanging in their statistical form. These stationary states give us the familiar shells of atomic structure, but they are not orbits. They are resonances, like notes on a violin string, defined not by motion through space, but by the shape of the field's vibration. And these vibrations are not confined to the electron alone. They are influenced by the electromagnetic field, by the presence of protons in the nucleus, by nearby electrons whose exclusion alters the available quantum states. The atom is not a solar system. It is a complex, interdependent symphony of fields tuned by invisible rules, played in a vacuum that is not empty, but alive with fluctuations. The vacuum itself is not silent. It seethes with virtual particles, Higgs excitations, quantum jitters. Even in empty space, the electron field exists everywhere, and your electron is a localized manifestation of that field. Its cloud is a standing wave, a probability distribution, a ghost in the lattice of existence. And this cloud is not spherical unless the energy state says so. In higher orbitals, the shapes become surreal, dumbbells, clovers, rings, not because the electron is carving those paths, but because the wave function allows those configurations. These shapes have been confirmed in laboratories, visualized through electron density mapping, seen not by looking at an electron, but by gathering its fingerprints across millions of observations. And so, the true image of the atom is not mechanical, but statistical, not planetary, but poetic. You are made not of tiny balls orbiting centers, but of smeared out whispers of probability, stabilized by the refusal of sameness, held together by abstract rules written not in stone, but in symmetry. And this vision of the electron, not as a thing in motion, but as a cloud of possibility, reshapes everything. It reshapes how we understand bonding. The covalent bond is not a link between two orbiting dots, but an overlapping of clouds, a sharing of probability. It reshapes how we understand electricity. The flow of current is not a parade of electrons rolling down a wire, but a migration of disturbances, guided by potential differences, shaped by quantum coherence. It reshapes how we understand light. Photons are emitted not by jumping electrons, but by collapsing wave functions, transitions between energy states in the cloud. And it reshapes how we understand ourselves. You are not made of things, but of relationships, of clouds, of potential. You are a superposition of memories and futures, a probability wave shaped by experience and observation. You are not a marble, but a mist. And the world you touch is not solid, but agreed upon. A dance of unmeasured states collapsed into temporary certainty. The electron doesn't orbit, and neither do you. You don't circle the center of your life in fixed paths. You hover, you shift, you resonate. Your presence is not a place, but a pattern. And perhaps that is the deeper truth of quantum mechanics. That the world is not made of stuff, but of structure. Not of orbits, but of options. Not of certainty, but of meaning drawn from uncertainty. The clouds that form atoms are the same. Clouds that form thoughts, uncertain, shifting, beautiful. And in the heart of every atom, the lesson is the same. What you see is only what was measured. What exists is what was possible. And the rest, vast and invisible, remains a cloud, waiting. The quantum vacuum has pressure and density. Picture a quiet, abandoned cathedral, tall, empty, echoing with stillness, where even your footsteps seem too loud, too intrusive. You stand in its center, convinced you're alone, surrounded by nothing but silence and void. But then you notice something odd. The air feels heavy. A pressure presses against your skin. The walls seem to shimmer ever so slightly. You hear the faintest hum, as though the silence itself is singing. This cathedral, you realize, is not truly empty. It only looks that way. Beneath its stillness is a hidden orchestra playing just below the threshold of perception. A presence, embedded in the absence, a fullness disguised as nothing. This is the quantum vacuum, and it too is no mere emptiness. In physics, the word vacuum conjures a misleading image, a space cleared of all matter, all particles, all activity, a barren background against which the drama of the universe unfolds. But quantum field theory has overthrown that notion with a quiet revolution. The vacuum, according to our best understanding, is not empty. It is the ground state of all quantum fields, the lowest possible energy configuration. But it is not zero energy, and it is not inert. It is a frothing sea of fluctuations, a storm beneath stillness, a ceaseless jitter of virtual particles momentarily emerging and annihilating, never seen directly, but constantly influencing reality. This vacuum possesses pressure. It possesses density. It has weight, consequence, and curvature. It is not a passive stage. It is a character in the cosmic play. And its presence shapes the universe more than stars, more than matter, more than light. The quantum vacuum determines the expansion of space itself. Its energy density contributes to the cosmological constant, the mysterious force we call dark energy, which drives galaxies apart with ever-accelerating speed. The vacuum's pressure is negative, a peculiar feature that doesn't pull, but pushes. It exerts an outward force, repelling rather than attracting, stretching the fabric of space-time like an inflating balloon. And this negative pressure is not theoretical poetry. It is measurable in the movement of galaxies, in the anisotropies of the cosmic microwave background, in the redshift of light from distant supernovae. It is the quiet power beneath the universe's roar. But how can a vacuum, a nothing, have pressure and density? Because in quantum physics, fields are fundamental. Every point in space is filled with fields. The electromagnetic field, the electron field, the Higgs field, the gluon field. And even when no particles are present, these fields remain. They never vanish. Even their lowest energy states, their ground states, are not truly zero. Instead, they ripple with zero-point energy, the unavoidable, irreducible fluctuations dictated by the uncertainty principle. This jitter cannot be eliminated. It is a built-in hum in the fabric of reality. Imagine a violin string stretched taut, but untouched. Even when no bow pulls across it, it vibrates faintly, imperceptibly, due to quantum uncertainty. That is the vacuum, a field that cannot sit completely still. And these fluctuations are not mere mathematical artifacts. They produce real effects. In the Casimir effect, two metal plates placed close together in a vacuum experience a measurable force, not because particles are pushing them, but because the vacuum modes of the electromagnetic field are altered between the plates. Fewer fluctuations can exist in the narrow gap, and the imbalance creates pressure. Nothingness, quite literally, pushes. In the Lamb shift, the energy levels of electrons in hydrogen atoms are shifted due to their interaction with vacuum fluctuations. Even the behavior of particle masses and couplings depends on vacuum polarization, the way the vacuum reshapes the environment around a particle. These are not edge cases, they are foundational. The quantum vacuum is the scaffolding of everything. And then there is the Higgs field, perhaps the most famous vacuum of all. It permeates space with a constant, non-zero value. Particles like electrons and quarks acquire mass, not because they contain mass inherently, but because they interact with this ever-present field. Without the Higgs field's vacuum expectation value, the universe would be filled with massless particles zipping around at the speed of light, incapable of forming atoms, molecules, stars, or life. The vacuum, then, gives form. It gives substance. It is the silent sculptor of existence. And yet, this vacuum is not the same everywhere. In the early universe, it underwent a series of phase transitions, shifts in the configuration of fields that redefined the properties of matter. As the universe cooled, the vacuum changed state, like water freezing into ice, and with each transition, new forces and particles emerged. The electroweak symmetry broke, splitting the electromagnetic and weak forces. The Higgs field settled into its current value. The very constants of nature, the masses of particles, the strength of forces, are frozen echoes of the vacuum's past transitions. What we call laws of physics are, in some sense, just the properties of our current vacuum. Change the vacuum, and the laws change. Imagine standing in a world where the vacuum had settled differently, where the Higgs field had a different value, where the strong force held less tightly, where photons had mass. The universe would look nothing like this one. There would be no chemistry, no stars, no us. That is how profoundly the vacuum defines reality, and yet we barely notice it. It is the quiet breath beneath being, the unseen weight beneath form. But if it vanished, if it changed even slightly, everything would dissolve. The vacuum is not passive. It is not optional. It is not nothing. It is the womb of all somethings. And this realization blurs the boundaries between existence and non-existence. If the vacuum is not empty, then what is emptiness? If pressure and density can arise from fields that contain no particles, then what defines reality? We have always drawn lines between something and nothing, between presence and absence. But quantum field theory erases that border. Even the void is full. Even silence is a song. And perhaps that explains why the universe is not static. Why it expands. Why it evolves. Because the vacuum itself has energy, and energy curves space-time, and space-time in motion cannot rest. The universe is not flying through emptiness. It is riding a wave of vacuum energy, pushed forward by the pressure of the void. And that pressure may never relent. The future of the cosmos, whether it expands forever, rips apart, or collapses, may depend not on stars or gravity, but on the properties of the vacuum, on the weight of nothing, on the shape of silence. So next time you think of space as empty, remember this. Between every planet and every star, between every atom and every cell, between your hand and your heart, the vacuum sings. It breathes. It bends light and lifts metal plates. It gives mass and takes shape. It presses outward on the universe like a wind without air, a tide without water. It is the true background of being. And perhaps, just perhaps, the vacuum is not a void at all, but a presence so fundamental, so stable, so omnipresent, that we mistake it for nothing only because it is everything. Particles have no set properties until measured. Imagine a library where none of the books have titles until you reach out to touch them, where the pages remain unwritten until your fingers graze the cover, and the moment you choose a volume, its content crystallizes from a haze of possibility into a fixed narrative. Before that instant, every book contains every story. Every character lives and dies. Every ending is happy and tragic. Every word is both spoken and unwritten. This is not fantasy. It is the universe you live in. At the quantum level, particles do not have set properties waiting to be revealed. They exist in a superposition of all allowable states, a shimmering sea of maybes and might-have-beens. An electron is not spinning up or down. It is both and neither until you measure its spin. A photon is not traveling one path or another. It is traveling all paths simultaneously, interfering with itself until you observe it. In quantum mechanics, reality does not exist independently of measurement. It is forged in the act of observation. Properties like position, momentum, spin, polarization, things you would expect to be intrinsic, factual, already decided, simply do not have defined values until measured. This isn't an abstract philosophical claim. It's what the mathematics and the experiments both demand. The double-slit experiment, a cornerstone of quantum mechanics, tells us that when you send a single photon or electron through two slits, it behaves like a wave, not choosing one path, but exploring both. An interference pattern forms, as if each particle interferes with itself. But if you try to observe which slit it goes through, if you demand a set answer, the interference vanishes. The pattern collapses into a pair of clumps, as if this particle was forced to choose. Your act of asking the question changes the answer. More than that, it creates the answer. And this is the philosophical heart of the quantum world, that particles are not tiny billiard balls with secret properties, hidden until we look. They are waves of probability, mathematical descriptions of all possible outcomes, until one becomes real through measurement. This isn't just weird, it's revolutionary. In classical physics, properties are objective. A rock has a mass whether or not you weigh it. A planet has a location whether or not you point a telescope at it. But in quantum physics, the particle doesn't have a position until you measure it. Its mass may be constant, but its momentum, energy, angular momentum, all of these can exist in superposition. The particle is not merely unknown before you measure it. It is undefinable, and when you do measure, you collapse the wave function, the mathematical object that contains all probabilities, into a single outcome. But why that outcome and not another? And what causes the collapse? That remains one of the deepest mysteries in physics, the infamous measurement problem. But one thing is clear, the properties we observe are not merely revealed, they are brought into being by the act of observation. The quantum world is participatory. And this participatory, nature challenges our deepest intuitions. It suggests that reality is not a fixed stage on which particles perform. It is a dynamic interplay between system and observer, between question and answer, between what is and what could be. When you measure the spin of an electron along the z-axis and find it to be up, that property becomes real, but only because you asked. Measure along a different axis, and the answer might be entirely different. The electron does not carry a hidden instruction manual saying, if asked this, answer that. It carries a set of probabilities, a toolkit of potential responses, and only when you measure do you force a choice. This is the crux of the Cauchy-Specker theorem. There is no consistent set of pre-existing values for all observables. You cannot assign fixed properties to a quantum system independent of the context in which you choose to observe it. Reality is contextual. It depends on your questions, and that makes you, the observer, part of the experiment in a profound way. You do not stand outside reality, passively watching. You are a participant. Your choices, your measurements, your frameworks, these help shape what is real. And yet, for all its strangeness, quantum theory works. It predicts with staggering accuracy. It powers our electronics, our lasers, our MRI machines. It gives us quantum tunneling, quantum entanglement, quantum teleportation. It matches experiment after experiment, never faltering, never flinching. The math says particles don't have properties until measured, and nature agrees. This isn't a failure of understanding. It's a deeper understanding than classical physics ever offered, and the implications ripple outward. If the properties of a particle depend on measurement, then reality itself is not absolute. It is relational. It is not a block of facts waiting to be read, but a living story written moment by moment. What you see depends on how you look. What you find depends on what you ask. And this is not just true for electrons and photons. It may be true for consciousness, for identity, for the self. You are not a fixed point in space. You are a superposition of roles, identities, potentials. You become specific, teacher, student, friend, stranger, only in interaction. Just as the electron has no set spin until measured, perhaps you have no fixed essence until called upon. Perhaps we are all quantum beings, stabilized not by certainty, but by context. And yet, in our world, measurement seems to solidify things. It gives us facts, it gives us data. But underneath those facts is a sea of uncertainty, a hidden depth of unrealized alternatives. Every time you observe, you collapse the wave, but only once. You do not see the other outcomes, the other realities, the other versions that could have been. They vanish or hide or drift into parallel branches, depending on your interpretation of quantum mechanics. Many worlds says they happen elsewhere. Copenhagen says they never existed. Objective collapse says the universe chose randomly. And all of them agree, the particle had no set properties before you looked. The implications are staggering. The fabric of the universe is not woven from threads of being, but from waves of maybe. And that maybe is not weak. It is the strongest thing we know. It is the source of all structure, all chemistry, all life. It is the ghost in every atom, the whisper beneath every certainty. Your body is made of atoms, each atom made of electrons, protons, neutrons, and each of those, quantum ghosts, undefined until measured. The solidity of your hand is built on probabilities stacked so precisely they feel like fact. But zoom in far enough and the edges blur. The core evaporates, the certainty dissolves, and what remains is a question, a wave, a choice waiting to be made. And so, perhaps the final lesson is this. We do not live in a universe of things, but in a universe of questions. Particles do not exist as fixed facts. They emerge from the fog only when we reach into it. And reality is not a structure we find, but a possibility we participate in. You are not simply watching the universe. You are helping it decide what it is. Every observation is a vote, a ripple, a collapse. You are the story choosing its own sentence, and the particles, those flickering points of presence, are the words that wait to be written, not by chance, but by choice.